This particular chapter is the chapter which is very simple, at the same time is having good amount of weightage in both mains as well as in advance. Hello students, this is your friend Sumit and today I am going to discuss topic 10 of the series, that is electromagnetic induction. This particular chapter is having a good weightage. As I mentioned, if in mains, if we talk about, we can expect up to 2 questions or at least 1 question from this particular topic. Few of the subtopics are very much asked of this particular topic, that are the Faraday's law, the motional EMF, mutual inductance questions and the LR circuit questions. These are very much asked, and in this video I'm going to discuss all the details of these particular topics and the other topics as well. With that, I'll show you the varieties of the questions JEE Mains has asked so far and which are expected in 2026. With that, I'll give you handpicked set of questions for your practice, because watching me solving the questions is not enough. You also need to practice the question yourself. So from the link given in the description box, you can go to the PW app, and as you know, PW app is the platform which is most trusted platform by the top rankers. So from there you can access the practice sheets, the DPPs and the class notes. Class notes will help you to revise the chapter very quickly. At the same time, the practice sheet will help you to have good amount of practice in the questions which are expected. Okay, so let us begin the discussion. We will be covering all the details of this chapter. I have mentioned some major topics: magnetic flux, the Faraday's law, then the motional EMF. We will be covering the inductance thing, how to find the self-inductance, how to find mutual inductance, then LR circuit, and finally the LC oscillations. Okay, so let us begin with the magnetic flux. Now electric flux we have understood, and we know what is electric flux, what is its formula. What electric flux basically gives us? It gives us the count, the number of electric field lines that are passing through an area. Mainly we say that electric flux is proportional to that count. Okay, so same thing with magnetic flux. Okay, so magnetic field lines are there, area is there, so magnetic flux is, it will be proportional to the number of magnetic field lines that are passing through this area. What is the formula of electric flux? E dot A. What will be the formula of magnetic flux? B dot A. Okay, so when we write magnetic flux we use phi. Okay, now phi we were using for electric flux also, so sometimes we mention specifically like this. If there is some confusion, we'll write B there. Otherwise, if it is understood that it is going to be magnetic flux only, we just write phi. Okay, so what is that? This is B dot A. A is my area vector, and area vector is perpendicular to the surface area. Here we are having a circular area, let us take like this. So the area vector of this is perpendicular to the surface area. Okay, and if let us take some non-uniform kind of shape is there, from there we need to find the flux. So what we do? We do integration. So we write there phi is equals to integration of B dot ds or dA, anything. Sometimes we use S, sometimes we use A, so I can write as B dot dA also, same thing. Okay, so this is how we will get the flux. So what is the unit of magnetic flux? So unit of B is Tesla, SI unit of A is meter square. So if I talk about SI unit, so it will become Tesla meter square. And Tesla meter square is also known as Weber. Okay, and that we denote with WB. So it is same as WB. Okay, Weber. So we say 1 Tesla meter square is equal to 1 Weber. Sometimes you may find Tesla meter square, or sometimes you may find Weber. Okay, so let us do some exercise on this. Now let me give you a question. Okay, so first the magnetic flux is magnetic field is given to us, and let us take that B is given as 2I cap plus 3J cap, okay, plus 9K cap, and this is in Tesla. This is the unit. Okay, so this is the magnetic field, and let us take the area is given to us. We may consider there is a square loop in XY plane. Okay, a square loop So I'll write here, find magnetic flux through a square loop of side 2 meter in xy plane. Okay, now how we will do this? We'll use the formula that magnetic flux phi b is equals to b dot a. B is given, we need to write a also. Now how to write a? This loop is present in xy plane. Now when I draw the area vector will be perpendicular to the surface area. So surface of the loop is in xy plane, perpendicular to it will be k cap. So when I write area vector here, so I'll say that will be the area, that is 2 into 2, that becomes 4. So this is 4 meter square k cap. Getting it? Now just do b dot a. So when we write phi, I'll say that is b dot a. And what it is, b dot a, so this is 2i cap plus 3j cap plus 9k cap dot with for k cap. How we take the dot product? So I cap will become 0, j cap will become 0. Okay, so for k cap, this will become 9 into 4, 36. So this is 36. What is the unit? Tesla meter square or Weber. This becomes my magnetic flux. Now it may be given like the formula I mentioned as b dot a. So I can write this as ba cos theta also. This is when magnetic field is constant. I can write this when the magnetic field is constant. Okay, so for b is equals to constant. If b is variable, we need to use like this. Okay, or maybe some non-uniform shape is there, so we can use like this integration of b dot a. From there we'll get the total magnetic flux. Okay, let us take some another example. Another example is I am taking a current carrying wire, okay, like this. It is carrying current in this direction and we are having a square loop in the same plane of the wire whose side is A, and this is at a distance say like this. Okay, here the current is I and the question is find the magnetic flux through the square loop. Okay, now here I cannot use b dot a or directly ba cos theta. Why? Because b is not constant. If you see, as the distance from the wire will change, the magnetic field will change. What is the formula? Mu naught I by 2 pi r. Okay, so as the distance, the r will change, the magnetic field will change. So you cannot take a magnetic field and just multiply with this area. No, not like that. So what we need to do? We need to do integration. Now for integration, you need to think. Here what I am going to do is, at a distance x from here, I will take a strip, because on this strip the magnetic field is same everywhere. Okay, so I am taking this strip which is having thickness dx. So for this strip, if I write the magnetic flux d phi, what will be that? That will be b dot dA, like this. What is b? B is inside the plane, and how much is that? Mu naught I by 2 pi 2 pi x. Okay, so mu naught I by 2 pi x, that is inside the plane. And what is the area vector? Okay, so if perpendicular to it, I can take outside also, okay, or I can take inside anyways. So one flux, if we see, the magnetic field is going inside. Okay, magnetic field is going inside it. I'm just going to write the magnitude only of the magnetic flux. So that is, I'll take inside only. So what will be that? That is A into dx. So area is A into dx and the direction is same. Therefore, that cos theta, so cos 0, that becomes 1. Simple. Now integrate it. X goes from A to 2A. X goes from A to 2A. And this will become mu naught IA by 2 pi. Integration of 1 by x. This mu naught IA by 2 pi is constant. I took it outside. 1 by x integration will be ln x. Limit from A to 2A. So this will become mu naught IA by 2 pi ln 2. And this becomes my magnetic flux through this square loop. Easy? Simple. Okay. Now let us discuss about the Faraday's experiment. So Faraday was doing some experiment and accidentally it is said that what happened is he threw a magnet through a coil, okay, which was connected to a galvanometer. So there was a coil like this. Connected to a galvanometer, okay. So here let us take it like this. We are having a galvanometer here and a magnet, bar magnet. Let us take this is north, this is south. It is moved like this. So what happens? There was deflection in the galvanometer. When it was moved in the opposite direction, there was deflection in the galvanometer in the opposite direction. Okay. And next, instead of having a bar magnet, he took 2 loops. Okay. One current carrying loop he took like this, another same. Now in this case also he moved it like this. Again there was deflection. He moved in the opposite direction. There was deflection in the galvanometer. And the third one was he had 2 loops. Like this. He switched it on, there was a momentary deflection. Switched it off, again there was a momentary deflection. So what was the conclusion from here? The conclusion was when the magnetic flux is changing in this loop, there was induced EMF or the induced current was there, which was detected by the galvanometer. Okay, so it is not due to the flux, it is due to change in flux. Why? When I closed it, there is a change from 0 to some magnetic flux phi. Okay, there was momentary deflection. After that the flux is constant, there was no deflection. Therefore there was a momentary deflection only when the change was there. Here change was there, momentary deflection, again the deflection becomes 0. When you switch it off, again there was a change in the magnetic flux from phi to 0. Okay, so there was momentary change, so a deflection, and again the 0 was constant further, therefore the deflection was not there. So when change is there, the magnet is there, if you keep this magnet stationary, not moving, there will not be any induced current. When the magnet is moving means the flux is changing through this loop, there is a induced current. And same thing here. So the point to understand is the induced current or the induced EMF will be only when the magnetic flux is changing. Okay, not due to the magnetic flux, it is due to the change of the magnetic flux. Yeah, that is the point. So according to Faraday's law, the induced EMF is equals to minus d phi by dt. So what is d phi by dt? Rate of change of magnetic flux with respect to time. When the flux is changing, there will be induced EMF. Now you'll ask, sir, why the negative sign is there? We'll come to that discussion. Okay, so first, as of now, keep this in mind that the induced EMF is equal to minus of d phi by dt. Very important formula. Now, flux we know that is I'm considering B to be uniform, then we can say this is B dot A, and if it is non-uniform, B dot dA like this. Okay, and then you differentiate it, you'll get the induced EMF. We'll come to some questions first, and then we'll see how this flux can be changed. Now, let us come back again. Now, flux depends on magnetic field, it depends on area, and it depends on the angle between the area and the magnetic field. So, there can be many ways to change the flux. One of the way can be when B is changing. Another way can be when area is changing. Another way can be when angle between B and A is changing. Okay. So, all the combinations will come to that. First of all, let us discuss few questions. So, the magnetic flux phi linked with a closed circuit of resistance 8 ohm varies with time as phi is equals to 5t square minus 36t plus 1. The induced current in the circuit at t is equals to 2s. Okay, find the induced EMF. So, I will say induced EMF is equals to minus of d phi by dt. You know how to differentiate? Okay, do that. So, minus d by dt of, put phi here, this is 5t square minus 36t plus 1. Okay, now when I differentiate 5t square term, 5 is constant, that will come out. Differentiation of t square is 2t. So, minus this will become 5 into 2, that is 10t. Again, differentiation of 36t is just 36. 36 will come out. Okay, differentiation of t is 1. So, this is minus 36 here. Differentiation of 1 is 0. So, plus 0 there. This becomes my induced EMF. Now, at t is equals to 2, we need to find the current. So, at t is equals to 2, if I write the value, how much is the induced EMF? So, that is minus of 10 into 2 is 20 and minus 36. 20 minus 36 is minus of 16. So, minus minus plus 16. 16 volt. Okay. Now, current we need to write. So, current is equals to, this is my induced current. So, induced current will be induced EMF divided by the resistance. So, what is the resistance? Resistance is 8 ohm. Induced EMF is this 16. So, 16 by 8, this becomes 2 ampere. Okay. Is this clear? Okay. Another question. In a coil of resistance 8 ohm, the magnetic flux due to an external magnetic field varies like this. So, again, this is a function of time. We can differentiate to find the induced EMF. The value of total heat produced in the coil till the flux becomes 0. Now, total heat produced, heat will be produced due to the current. Okay, current is moving through a resistor. So, what is the power they are dissipated? That is I square R. Okay, so we need to integrate I square R. I will be changing because induced EMF will also be changing. Until what time we need to integrate? It is mentioned here. Till flux becomes 0. Flux becomes 0 means put this is equals to 0. If I put phi is equals to 0, what is the time? So, 9 minus t square is equals to 0 basically. T is equals to plus minus 3. We will take 3. Why so? Time is always positive. Okay, so t is equals to 3 we will take. Now, what is the induced till t is equals to 3 means I need to integrate from 0 second till 3 seconds. I need to find the total heat in this interval from 0 second to 3 second. Okay, now at any instant t, what is the induced EMF? Induced EMF is equals to d phi minus d phi by dt. Differentiate this. This will become differentiation of t square is 2t. Okay, so this will become minus of 40 by 3. Minus, sign was already there, again minus, and this is 4t by 3. So this becomes basically 4t by 3. This is my induced EMF. Now, what is the induced current? So, if I write induced current, that is induced EMF divided by the resistance. So, 4 into 2, so this is t by 6 ampere. I got current. How much power dissipated? I square R. Now, put that I square, T by 6 square into R is 8, I square R. Or I would have written other way also, V square by R, like that also I would have written. So this is I square R, this is my power, and what is heat? Power integration of P dt. So this is P dt integrated, this will become my heat, and what is the interval? From 0 to 3 seconds. 0 to 3 seconds. Now we need to integrate it and solve it to get the answer. I am leaving this for you. Do this calculation and make sure you comment your answer. Okay, I need to see how many students are parallelly solving the questions with me. Okay, now as I discussed, there can be many ways of changing the flux. First can be when B is changing with time. Okay, another thing is when area is changing. And the next can be when my theta is changing, or I can say when the orientation, theta means the orientation between the area and the magnetic flux. Theta is the angle between the area vector and the magnetic flux. Okay, so when the orientation of the loop is changing, theta is changing, area remains same there, magnetic flux remains same, only theta can change. Okay, that way also induced EMF can come. We'll come to some questions on each of them. So first case, if magnetic field is a function of time. Now when we write induced EMF, we say that is minus d phi by dt. Okay, now if induced EMF is a function of time, then B will vary, A will remain same, B is changing. Okay, if B is changing, in that case area is constant, we can take that out, integration of dV by differentiation of B with respect to time will remain there. Okay, so again I am writing that this I am writing for B constant. Okay, not B constant, B is changing here with time. Okay, but with reason, or I'll say with coordinates. Okay, in space it is constant. When it is in space it is constant, I can use the formula B dot A. Okay, so this will become E is equals to minus of d by dt of B dot A. Okay, so I'll write this as BA cos theta. This is minus d by dt of BA cos of theta. B is changing, A cos theta dB by dt with a negative sign. Okay, so here I'm saying that my B is constant in space. There I can use it. B dot A. When I'm writing B dot A, I'm considering B is everywhere throughout the you can say my area. Therefore, I'm saying B is constant in space but varying with time. Then I can use this. Or in general, you find flux. If let us take B is not constant throughout the space, B is changing. Let us take the example of wire. As saying the wire was there, the wire is carrying a current. Okay, let us take the current is changing. It means B will be changing with time. Okay, and here B is not constant in space also. So B is changing throughout this loop also. So there what we need to do? We need to integrate. We need to integrate to get phi. Okay, we'll get phi, we'll put phi there and we'll differentiate it to get the induced EMF at a particular instant. Some examples. Okay, a coil is placed perpendicular to a magnetic field of 5000 Tesla. When the field is changed to 3000 in 2 seconds, an induced EMF of 22 volt is produced in the coil. Okay, if the diameter of the coil is this, then the number of turns in the coil is. Okay, using the formula, I'll say that induced EMF is equals to minus of d phi by dt. Coil is placed perpendicular to the magnetic field. It means what? Area vector is making 0-degree angle with the magnetic field. Means the magnetic field is perpendicular to the surface area. Area vector is perpendicular to the surface area. So what does it mean? Angle between area vector and the magnetic field is 0. So when I say phi, that is BA cos theta is 1 because theta is 0. So it is just minus of d by dt of B into A. Now here it is giving an interval. It is saying that the magnetic field is changing from 5000 Tesla to 3000 Tesla in 2 seconds. Now I cannot use differentiation. What I need to use? Del there. My area is constant anyways, so I'll first write this as A into dB by dt. Okay. So for dB by dt, I'll write this as A into del B by del T. Like this. Okay. Now this is del B by del T. What is del B? Del B will be 5000 was initial, changed to 3000. So 3000 minus 5000 is 2000 minus. So minus 2000. Okay. What is area? Diameter is given. From there we need to find the area. Okay. So this is my del B. Okay. This is my del B. And what is del T? Del T is 2. So 2. This is my del B by del T into area. A negative sign is also there. Area will be pi d square by 4, or diameter is given. I can find radius. What will be radius? 0.01. So I can write area as pi r square. So pi into r square. This r is 0.01. When you do square, so this will become 1 into 10 to the power minus 4. This 10 to the power minus 2. Square will be 10 to the power minus 4. Everything is fine. Okay. And what else? Okay, everything is fine, I hope. So minus minus, this will become plus. This is 1000, and 10 to the power 3 will cancel. So this will become 10 to the power minus 1. So this will become pi by 10. Okay, so this is pi by 10. This is then the number of turns. Okay, number of turns is also there. Induced EMF is given to us 22. Number of turns is there. If number of turns will be there, when we write flux, it will become n times because each turn is having that much flux. If number of turns is n, so we'll multiply that with n. Okay, we'll multiply this with n. Number of turns is there, we'll multiply this with n. Here we'll multiply n. Here n will come. Here my n will come like this. And this is given to us as 22. Okay, I can put pi as 22 by 7, and from there what will be n? So 22 is equals to pi is 22 by 70 there into n. So n comes out to be 70. D. If a coil is there, okay, try to understand that thing. If a coil is there, if one you can say loop is there, what will flux? We will say there V dot A. Now if the number of turns become n times, how much will be the flux? Flux will also get n times. Okay, so in this formula, when we are saying induced EMF, okay, so when we are saying this phi, either you can say this phi is my total flux, or you can say phi is the flux through the one coil into the number of the coil. So into n you have to do there. Number of the coil, or I'll say number of the turns in the coil. Okay, the conducting square loop is placed in xy plane in presence of magnetic field. Okay, that is this in SI unit. If the radius of the loop is 1 meter, the induced EMF in the loop at t is equals to 2 seconds. Again the same thing. First thing, the loop is placed in xy plane. Okay, the loop is placed in xy plane. It means the area vector will be along k cap. That is clear to us. Magnetic field is given to us. This is my magnetic field. The radius of the loop is given. So when I write area, I'll say that is pi into r square. Okay, how much is that? Pi into r square. So that will become just pi r is 1. So when I say area vector, so I'll say this is my pi k cap. Okay, when I say B is my 3t cube I cap plus 3t square k cap. Okay, you see, I am saying that my induced EMF is minus d phi by dt. Phi is b dot a, okay, and area is constant. I'll take that out, a dot d by dt of b. Or anyways, first you can take dot product, then you can differentiate, or first you can differentiate, then you can take dot product. It's the same thing. Okay, so if I take the, let us take the dot product first, because when I take the dot product first, this term will go. Okay, only pi into 3t square will remain. So I induce, if E induce when I'll write, so this is minus d by dt of pi 3 pi t cube. Just this thing. 3 pi is constant, I can take that out. Differentiation of t cube will become 3t square. So this becomes minus 9 pi t square. Okay, and okay, how many number of turns are there? That is 1. That is not mentioned, it means that is 1. The induced EMF of the loop, we need to find that t is equals to 2 seconds. Now put t is equals to 2 there. So it will become minus 9 into 2 square is 4 pi. That is minus 36 pi. Okay. Don't okay, everything is fine, I hope. Yeah. So this is n pi, and comes out to be 36. You'll say there is a negative sign. No, you just need the magnitude. Negative sign tells us about the polarity. Okay, so we need how much is the induced EMF. So induced EMF will say that is my 36 pi. Let me see if I have done any calculation mistake here. 3t square k cap, and the area will be pi k cap. Okay, so this become 3 pi t cube. Okay, I did a mistake. What is that? This was 3t square. Yeah, I did a mistake. This was 3t square, not t cube. Here when I'm saying, when I was taking this dot product, okay, that was b dot a. So this was 3 pi t square. 3 pi t square. Yeah, this mistake I did. Dot product. Okay, this will get 0. So this will become 3 pi t square. When I differentiate this, this will become 3 pi is constant. That will come out, negative sign. Okay, t square differentiation is 2t. So this is minus of 6 pi into t. And now you put t is equal to 2. This will become minus 12 pi. And I just need the magnitude, so I'll say this is 12. Okay. Fine. Now, when area is a function of time, when area is changing with time, so we need to, like when we are saying that my flux is equals to b dot a. Okay, so when I say that my induced EMF is equals to minus of d phi by dt, area is a function of time. Okay, so b dot, I can say this is my dA by dt. Area is varying, I'll differentiate area term. Magnetic field is constant, I'll take that out. Now consider this question. A conducting square loop is placed in a uniform magnetic field of 0.4 Tesla. Magnetic field is given to us with its plane perpendicular to magnetic field. Okay, perpendicular to magnetic field means the angle between the area vector and the magnetic field is 0 degree. Somehow the radius of the loop start expanding at constant rate of 1 millimeter per second. The magnitude of induced EMF in the loop at an instant when radius of loop is 2 centimeter. Okay, so if I write the magnetic flux, what is that? B dot A. Anyways, area vector is parallel to magnetic field, so I'll say that is my B into A. So B is how much? 0.4. Okay, B dot A, that becomes my BA just, and B is 0.4, and what is area? Area is pi r square. I'm not putting the value of radius because the radius is changing here. So this becomes my flux. What is that? 0.4 pi r square. Now induced EMF I need to find, minus d phi by dt. Sorry. Okay, differentiate this. Minus, when I differentiate it, this will become 0.4 pi, r is variable, okay. I am differentiating r square with respect to t. So what I will do? Differentiate r square with respect to r into differentiate r square with respect to t. This is chain rule of differentiation. Getting it? Is this clear? I am differentiating this term, okay. So there is r, which is my variable. I have to differentiate r with respect to t. So what I did? Differentiate r square with respect to r first, then into differentiation of r with respect to t. Chain rule. Multiplying and divide with dr. Understand, like this? Okay. Now write it. So this will become minus 0.4 pi into r square differentiation will become 2r. This is 2r into dr by dt. What is dr by dt? This. It is expanding, it means dr by dt is positive. So dr by dt is 1 millimeter per second. If I convert that to SI, so I'll say 1 into 10 to the power minus 3 meter per second. Okay. Put the values. So this is 0.4. I'm not taking the sign, just I need the magnitude. 0.4 into pi into 2 into r. What is r? At the instant when r is 2 centimeter. So 2 centimeter it is. So 4 pi into 2 centimeters. So 2 into 10 to the power minus 2. Yeah. Into dr by dt. dr by dt is 1 into 10 to the power minus 3. Yeah. Now you can calculate it. Put your answer in the comments. Okay. I hope the concept is clear to you. Very clear. Now when angle is changing between B and A, let us take, I write phi, this is B dot A, which I write as BA cos of theta. Here theta is changing. When I say d phi by dt, E induced as negative of this, so this is minus d by dt of BA cos of theta. Okay. BA is constant, I'll take that out, minus BA d by dt of cos of theta. Now in questions, there may be given to you how theta is changing. Let us take theta is a function of time, some angular velocity there which is constant. So you may write theta is equals to omega t, like that. Okay, and we can put it there and we can differentiate it accordingly. We'll do some questions, you'll understand that in a better way. Now see this question. A coil of 200 turns and area 0.2 meter square is rotated at half revolution per second and is placed in a uniform magnetic field of 0.01 perpendicular to the axis of the coil. Perpendicular to the axis of the coil means what? Angle is 0. Yeah. The maximum voltage generated in the coil is this. Okay. Now, half revolution per second, okay, is rotated at half revolution per second. This thing, you see. This is how the coil is rotated and is placed in uniform magnetic field perpendicular to the axis of coil. Sorry, here this is not perpendicular to the plane of the coil. The magnetic field is perpendicular to the axis of the coil. Axis of the coil means about which I am going to rotate it. That is the point. I am going to rotate the coil about an axis, that is the axis of the coil, and the magnetic field is perpendicular to that axis. Is that thing clear? Yeah. Now we are rotating it with a constant angular speed, and what is that angular speed? Half revolution per second is given. From there we need to find omega. What is omega? half, omega is radian per second. How many radian per second? So it is saying half revolution per second. Half revolution means pi angles. Complete revolution means 2 pi angle. So half revolution means pi angle. So I'll say this is my pi radian per second. I got my omega. Is this clear? Now, when I write my induced EMF, okay, when I say E is equals to minus of d phi by dt, and phi is BA cos theta and theta is omega t. Theta is omega t. Omega is given to us. Okay. Now when I differentiate this, this will become minus BA omega. What is differentiation of cos omega t? First of all, what is differentiation of cos omega t? Differentiation of cos theta is sin theta, differentiation is cos theta. Cos theta differentiation is minus sin theta. So cos theta differentiation is minus sin theta. Now differentiation of cos omega t will be minus omega sin omega t. So minus minus will come plus, it will become plus omega into sin omega t, like this. What we need? The maximum voltage. I need the maximum means the peak of this. What is that? That is this thing. I need this. So when I say E max, that is my B into A into omega. What is B? B is 0.01. What is area? Pi into R square. Okay, no, area is given to us directly. 0.2. 0.2 into what is omega? Omega is pi radian per second. This is fine? Yeah. So 0.2, and one more thing I missed. 200 turns. Turns is there, we need to multiply this with n. We need to multiply this with n. I need to multiply this with n. Here n will come. Here n will come. And here n will come. So into 200. Now this 2 zeros, this got cancelled. Okay, so this will become 0.4 pi. 0.4 pi you can write as 4 pi by 10 or 2 pi by 5. 2 pi by 5 means my beta becomes 5. Sometimes we miss this thing, the number of turns thing. So keep that in mind while solving the questions. If number of turns is given in the question, your induced EMF, you need to multiply d phi by dt with n. Okay, another question we are having. A square shaped coil of area 70 centimeter having 600 turns rotates in a magnetic field of 0.4. This is my magnetic field about an axis which is parallel to one of the side of the coil. So you can say this is my square shaped coil and I'm going to rotate it about an axis parallel to one of the sides, which is that, you may consider it like this. Okay, so I'm rotating it like this, and magnetic field about an axis which is parallel to one of the sides of the coil and perpendicular to the direction of field. Yeah, perpendicular to the direction of field means my field is perpendicular to the direction of the axis. Okay, so you can say consider the field to be perpendicular here, maybe down the plane or outside like this. Getting it? If the coil completes 500 revolutions in a time, now from 500 revolution in a minute, I need to find my omega. So omega is radian per second. So first of all, this is 500 revolutions. In each revolution, it is rotating 2 pi radians. So these many radians, and these radians in 1 minute. So I need to convert that to second. So divide by 60. So this becomes my radian per second. Getting it? 2 into 3. So this will become 50 pi by 3. Omega I got. the instantaneous EMF when plane of coil is inclined at an angle 60 degree with the field. The angle between field and coil is 60 degree. Field and coil is 60, not between field and area vector. It means the angle between field and area vector is 30 degree because area vector is perpendicular to the coil. So when I say angle between my field and area vector, that will be 30 degree. I write my flux as BA cos theta. Theta I am taking the angle between, okay. So theta as omega t. Getting it? And number of turns is 600, so I will multiply this with n also. When I differentiate it to find the induced EMF, what I need to find? The instantaneous EMF only. Okay. So minus d phi by dt, that is minus nba omega into sine. Okay, a negative sign will also come there, so plus. So into sine of omega t. Now this is my omega t at that instant, 30 degree. Put this. This is my 30 degree. What is my n? N is 600. What is b? B is, what was that? Yeah, 0.4. What is A? Area is 70 centimeters square, so convert that to meter square in 10 to the minus 4. What is omega? Omega is this, 50 pi by 3. And what is sine 30? That is 1 by 2. Put the values, solve it, and put pi is equal to 22 by 7. They are giving this. Use pi as 22 by 7 and then make sure you mention your answer. So in these questions, there can be multiple things you need to take care, like data is there, okay, number of turns might be there, some how the theta is varying, that is there, the area is there, the magnetic field is there, so many things is there. So we need to write each and every quantity properly. Next, charge flow in a circuit. So we mentioned that in a circuit, the induced EMF is given as minus d phi by dt. Okay, this is the induced EMF in a circuit where phi is the flux. Okay, we differentiate flux to find the induced EMF and negative sign is there. We got this point. Now, if I ask you what is the induced current, so you'll say induced current will be my induced EMF divided by resistance. So minus d phi by dt into R. This becomes my current. Okay, now let us write this equation again. So my I is equal to minus d phi by dt divided by R. Let us take dt on the other side. I dt, and this is minus d phi by R. Integrate it. Sorry, I did a mistake here. This was dt. This was my t. Okay. What is integration I dt? Charge. Yeah. Yes. That is my q. So q induced, I may write, okay, this is my charge induced and this is equals to minus. When you integrate d phi, so that will come out to be phi when you will put the limits initial to final. So that will become final minus initial. That gives us the change del phi divided by R. So this becomes my formula of induced charge. Make sure you keep this in mind. So induced charge is minus of del phi by R. Okay, let us do some questions. Again, we are having this question asked in 2019. A conducting circular loop of thin wire has area this, resistance this. It is placed perpendicular to time dependent magnetic field. Okay, this magnetic field is a sinusoidal. The field is uniform in space. Okay, uniform in space means you can use B dot A. Okay, the same point as I was mentioning initially. So when he's saying uniform in space, it means you can use formula B dot A. Uniform in space, then the net charge flowing through the loop during t is equals to 0 to t is equals to 10 milliseconds. So what I need del phi I'll say del phi by r. I just need the magnitude, negative, positive doesn't matter, I just need the magnitude. So del phi by r. What is del phi? Area is constant, so I'd say this is area. B is changing, del B by r. This is how I say. What is B at 0 second? If I write my B initial, put 0 there, it will become 0. Sin 0 is 0. If I write my B final, put T as 10 millisecond. So you put T as 10 milliseconds. So what it is 50 pi into 10 millisecond means divide with 1000. So this is basically pi by 2. Okay, so this becomes pi by 2. Sin pi by 2 is 1. So this will become 0.4 Tesla. So when I say A into del B is 0.4. Okay, B final 0.4 minus B initial 0 divided by R. What is area? Area is given 3.5 into 10 to the power minus 3. So 3.5 into 10 to the power minus 3 into, this is my area, okay, into this is my del B, which is 0.4, divided by my resistance. What is that? That is 10. Number of turns is given? No, that is not mentioned. When number of turns is not mentioned, it means that is 1. Now solve it. So what it is? I need to find in millicoulomb. So the options are in millicoulombs. So if I write this, it will become 10 to the power minus 4, minus 5, minus 6. So I'll say this is 10 to the power minus 6. This is 35 into 4. How much is that? 35 into 2 is 70 into 2. That will become 140. 140 divided by, okay, 140 only. At 10 I already considered. So this is 140 microcoulomb. And 140 microcoulomb means 0.14 millicoulomb. Yeah, that is correct. Getting it? Just find del phi. Now here B is varying with time. How it is varying doesn't matter. He just asking from t is equals to 0 to t is equals to 10 millisecond how much charge was induced. Okay, this is how much charge that was flow. Okay, I need to find. So I just need del phi. Doesn't matter how my B is changing. It may be changing sinusoidally or it is changing some other way. Doesn't matter. Just find del phi. Del phi divided by the resistance. Another question we are having. An insulated copper wire of 100 turns is wrapped around a wooden cylinder. Okay, core of a cylindrical core of cross section, that is 24 centimeter square. The two ends of the wire are connected to a resistor. Okay, let me do this one by one. First of all, insulated copper wire, number of turns is given as 100. So I'll write n is equals to 100. All the details I am writing now. Wrapped around a wooden cylinder, core of cross section area 24 centimeter square. So this is my wooden cylinder, okay, and I am wrapping it around like this. Like this. And what is the area? Area is 24 centimeter square. The two ends of the wire are connected to a resistor of resistance 12 ohm. So this wire is having two ends and we connected that with a resistance whose resistance is given as 12 ohm. If an externally applied uniform magnetic field in the core along the axis changes from 1.5 in one direction to 1.5 in opposite direction. So magnetic field was 1.5 in this direction and then finally it is 1.5 in the other direction. What does it mean? Field changed by 3 Tesla. Okay, I'll say plus 1.5 to minus 1.5 or minus 1.5 to plus 1.5. So but the total change is 3 Tesla. Yes. In the opposite direction, the charge flown through the through a point in the circuit during the change of the magnetic field will be. So what is del B? 3 Tesla. Del phi by R. What is del phi? N into del B into area divided by R. What is N? N is 100. Put it 100. What is del B? Del B is 3. I wrote that 3. into what is area? 24 centimeters square. So 24 into 10 to the power minus 4. Yes. Divided by the resistance. Resistance is 12 divided by 12. And I need to report my answer in millicoulomb. So 110 I'll cancel. So this will become 10 to the power minus 3. So this will become milli now. Okay. 12 into 2. So this will become 60. 12 into 2, 3 into 2, 6. This will become 60 millicoulomb. So the answer becomes 60. Is this clear? Okay. Now, coming to the point, sir, why the negative sign is there in E induced is equals to minus d phi by dt. Okay. So that is told by Lenz's law. So why the negative sign is there? The induced current that comes in a loop, it comes such a way that it try to oppose the change. I'm not saying it try to oppose the magnetic field. No, it try to oppose the change. That is the point. So if let us take magnetic field is increasing in a particular direction, so the induced current will come in such a way that it will apply magnetic field in opposite direction, so that it opposes the change. If a magnetic field is decreasing in a particular direction, the induced current will come in such a way that it applies its magnetic field in the same direction, such that it will oppose that decrease, right? Are you getting that point? Yeah, that is important to understand. It opposes the change. If something is decreasing, it will try to increase it such that the decrease will be less. If something is increasing, it will decrease it. Okay. Now, let us take this example. This is North Pole, this is my loop. I am moving this magnet towards this. It means the flux is increasing. In which direction? The field lines will be coming like this, okay. The flux through the coil is increasing, so the coil will try to oppose the change. It means it will decrease that. How to decrease? It will apply its own magnetic field in opposite direction. It will apply its own magnetic field in that direction such that it opposes that change. Now if you do the other thing, let us take, you are taking this magnet away. If you take this magnet away, the field in that direction is decreasing. It will apply its own magnetic field in the same direction, so the induced current will come in the opposite direction. Okay. Here the same thing. I am taking this north pole in the opposite direction. So the field that was there in this direction, okay, the flux that is passing through is decreasing. That flux is decreasing. It means it will try to support that. Something is decreasing, it will support that. Okay, support means it will apply in the same direction such that the decrease will be less. Okay, so its field lines was in this direction, it will also apply its field line in the same direction. The decrease will be less such that. That is the key. Okay, we are having some questions. Now, you are having this question on screen. I am giving you time. First, read it. Okay, let me read for you. A coil is placed in a magnetic field as shown. A current is induced in the coil B because now induced current direction is given to you. Now, which of the options can be possible? There can be multiple things, but which one of them is a possible case? You can answer it and then you can come back. I hope you commented your answer. Okay, you are back now. So induced current is coming in this direction. What can be possible thing? Possible thing is, let us take magnetic field is inside the plane, okay, and it is increasing. This is one thing. Magnetic field is inside. Magnetic inside means cross. Magnetic field is inside and increasing. Inside and increasing, therefore it applied its magnetic field outside to oppose the change. One thing. Other case can be magnetic field is outside and decreasing. Outside and decreasing. In that case, it will apply its own magnetic field outside such that it will oppose the decreasing. Getting it? Okay. So these two cases can be now come one by one. Outward and decreasing with time. No, outward and decreasing with time. First, this option, you see, outward and decreasing with time. He is saying this. I'll say this is correct. Parallel to the plane, no. If it is parallel to the plane, there is no linked flux. It will not come. Okay. Parallel to the plane of the coil, increasing, no. Last, outward and increasing with time. No, outward and decreasing. This is incorrect. Okay. Try to understand this option again. Outward, it is outward and decreasing. Therefore, the induced current is coming in such a way that it will apply its own field outward only. It is decreasing outward. It will apply its outward only to oppose the decreasing. Okay. Another question asked in JEE Mains 2020. A small bar magnet is moved through a coil at constant speed from one end to another. Which of the following series of observation will be seen on the galvanometer G attached across the coil? Three positions shown: the magnet entry, the magnet completely inside, the magnet exiting. Now one thing, magnet is entering, flux will be going inside, flux is changing, some deflection will come in one particular direction. Magnet is inside only, the flux will remain the same, flux will not change. When the magnet is inside, the flux will remain the same, it will not change. It means it will show zero deflection for B. When magnet is exiting, the flux will be decreasing. Okay, you may say, so the deflection that will come, that will be in the opposite direction. Initially when it was entering, okay, the flux was increasing, deflection was in a particular direction. When it is inside, the flux is not changing, deflection will remain zero. When it is exiting, the flux is decreasing. Okay, as the flux is decreasing, the deflection will be there but in the opposite direction. So in A and C, the deflection will be opposite. In B, the deflection will be zero. Come to the options. In B, the deflection will be zero. Deflection is zero. And in A and C, the deflection is opposite. Yeah, it is towards the right, it is towards the left. Is this clear? Yeah. In A and C, the deflection is opposite. In B, the deflection is zero. Now motional EMF. Let us take a conductor is there and that conductor is moving in a let us take magnetic field. Okay. Now there can be one thing, if some closed loop is there or some open loop is there, it can be, but I am considering just any section, any random section. I am moving this with velocity v. This is my velocity, okay, v is my velocity. I am denoting with small v, let us take, and some magnetic field is there, B, in a particular direction. Charges are there inside the wire. If you take any point charge, Q, some force will be there due to magnetic field. How much is that force? I'll say my magnetic force F is equals to Q V cross B. This is my force. Now this charge will move due to magnetic force, okay, and let us take it moved a distance dl along the wire, only it will move. It moved a distance dl. I ask you how much is the work done. You'll say work done is equals to F dot dr. Here it is dl, so I'll say work done dw, okay, in that is equals to my F dot dl. Okay, so what is that? Q V cross B dot dl. This is my work done. Work done per unit charge becomes my induced EMF in the dl length. Okay, so what is EMF? EMF means that let us take a charge is going from negative terminal to positive terminal. EMF is E. How much work it will be done? E into Q. Okay, so here the work done is my this. Okay, so per unit charge this becomes my induced EMF. So I will say my induced EMF. Okay, this is my DE on this length DL. Okay, so this becomes my DE. What is that? V cross B dot DL. If you need to find the total induced EMF in the length, just integrate it. So I'll say my induced EMF is equals to integration of V cross B dot L dot DL. Okay. V cross B dot DL. Simple. Now this can be done by other way also. You may consider a rod. Okay. Let us take, we are moving it in this direction. What will happen? On the electrons are there, some magnetic force will be there. So how much is that? QV, magnetic field is inside here. Okay, so QV cross B, V cross B. Okay, so magnetic force is coming in, Q is negative, so downward direction. So downward direction my magnetic force is coming. So at steady state, because we know this is a rod, so at steady state what should happen? The charges should not move. So an opposite electric field force will be there, or I'll say the force due to electric field will be there. Okay, which will set the equilibrium. The charges, negative charge will come down here, negative will accumulate there, positive will accumulate. Okay, net electric field will be induced. Okay, and that electric field will have electric forces. That electric forces will cancel out the magnetic force, that is Q V cross B. I'll say Q V cross B, that will cancel out my force due to electric field, that is my E into Q. Q got cancelled. Okay, if I talk about the sign also, I'll say the total force has to be 0. Total force has to, magnitude wise we can say both the magnitudes are equal, but if I talk about sign also, the total force has to be 0, and from here I got my electric field as V cross B, and I can say integration of E minus E dot dl is my induced EMF. So E induced is equals to minus of integration of E dot dl. Here there is a negative sign, so minus minus that will become plus, and this will become V cross B dot dl integration of this. Same thing. So keep this formula in mind. Okay, if you are having a rod which is moving, let us take a rod is there like this, magnetic field is like this, it is moving in this direction. Will there be induced EMF? If you do V cross B dot dl is 0, no induced EMF. If you are having a rod like this, okay, moving like this, and the magnetic field is also like this, V cross B is 0. So here my velocity and magnetic field, will say velocity and magnetic field, they should be perpendicular. That thing is there. Okay, and this cross product direction should be along the length. Getting it? It means I'm moving a rod like this. Will there be induced EMF? Yes. V cross B dot L. Okay. So my V, the velocity, and my magnetic field and my length, these three are these three are perpendicular to each other, the magnetic field, the induced EMF will be maximum. If there is some particular angle, the induced EMF can be there. I am not saying that they need to be always perpendicular. If some angle is there, the induced EMF will be there, okay, but that will not be maximum. I hope you got the point. So when I am saying that my rod is moving like this, which end will be positive, which end will be negative? I will do V cross B. B is inside, cross B. The thumb gives my direction of positive, plus this is negative. So when I'll ask you how much is the induced EMF in this, okay, and what is the polarity, then you need to find the polarity like this and write the induced EMF. Example. The same thing as I was saying. This is my rod. It is moving with velocity v in this direction, and my magnetic field, let us take, is inside the plane B. Now you tell me how much is the induced EMF. The length is L, and what is the polarity? So when I say V cross B dot L, okay, this V cross B, this comes out to be positive, this comes out to be negative. So effectively when I write, I can make a battery. Upper is positive, lower is negative. How much the magnitude? BVL. Here induced EMF is having magnitude BV into L. So effectively I can draw this rod like a battery. Just like in some circuit, let us take the rod is there, the rod is moving, some resistance is there. You are asked what is the induced current or all those things. Okay, we'll do those questions as well. And there what you can do is, in place of moving rod, you can show a battery. How much is the battery? Battery I got here BVL, and how much is how is the polarity? Polarity will get from V cross B. Upper is getting positive, lower is getting negative. So this is the polarity. Sometimes in question it is asked whether the current that will come will be clockwise or anti-clockwise. You can find that with using Lenz's law also. Okay, just see how the change should come such that it will oppose. How the induced current should come such that it will oppose the change. That way also you can find the direction of the induced current. Okay, motional EMF due to translational motion of conducting rod, we already discussed. Here a rod is moving, here let us take with velocity v, L is the length. Here if I use my formula v cross b dot dl, I integrate it like this. Okay, so v cross b dot dl, when I v cross b, b is inside, upper is coming positive, okay, lower is negative, and that is along the length only, so it will just become b v into L. Okay, upper is positive, lower is negative. So what I will do, I will draw a battery in place of this rod, and its EMF is BVL, V cross B dot L. I am doing this again and again. This is V cross B. Upper is positive, lower is negative. Keep this thing in mind. That is important. Okay, we are having that question now. What it is? 1 meter long metal rod XY completes the circuit as shown in the figure. The plane of the circuit is perpendicular to the magnetic field. The flux density, magnetic field of flux density 0.15. Okay, magnetic field of flux density means the magnetic field is 0.15 inside the plane here. If the resistance of the circuit is 5 ohm, the force needed to move the rod in direction as indicated. We are moving towards the right. So how much force is needed for that? And we are moving it with a constant speed of 4 meter per second. So you know, if there is a current carrying conductor, how much will be the force on the current carrying conductor? IL cross B, if B is uniform. So IL cross B. So what we need to find? Induced current. So first, for induced current, what we need to find? Induced EMF. Okay. So this is moving towards the right, V cross B dot L, up is positive, lower is negative, the magnitude is BVL. So I can just show a battery here, just a battery. This is a battery, induced EMF is BVL, my induced current will become the induced EMF by resistance. I got my induced current, that is BVL by R. Okay. Now how the current will be moving? The current will be moving like this, from it will be coming out of the positive terminal. Okay. Or other way, as this rod is moving towards the right, the flux is going inside the plane. Flux is increasing inside the plane, so it will apply its own field outside the plane to oppose it. Therefore also I can say the current will be moving like this. How much will be the force we need to apply? Here we are moving it with a constant speed. Magnetic field will be applying some force. We will be applying equal and opposite force as that of the magnetic field. Then only it will be moving with that speed. Okay. So what is the direction of magnetic field force? So I is there. I L cross B. So this is the direction of force due to magnetic field. And we need to apply force in this direction, equal and opposite. This is my external field. Then only the acceleration will be 0 and it will be moving with a constant speed. Is that clear? Yes. So I got my force, and how much is that force? Magnitude BIL in this case. What is I? I is BVL by R, so BL into BVL by R. So what it is? B square L square V by R. Okay, put the values. B is 0.15. Okay, I'm leaving it for you. So B is 0.15. What is L? L is 1. And what is V? V is 4 meter per second. And what is my R? R is 5 ohm. Okay, so put those values, solve it, and put your answer in the comments. I hope you got it. Okay, I'm moving ahead. Now another question, the magnetic field in region is given by this. Now here you see the magnetic field is changing with X. A square loop of side D is placed with its edge along XY axis. The loop is moved with a constant velocity V0 I cap. The EMF in the loop is. There are multiple ways to do this. We need to find the induced EMF. Now if the magnetic field is constant everywhere, and if there is a closed loop, what will be the induced EMF? 0. Okay. What I am saying is, if let us take closed loop is there, B is constant everywhere, and you are moving it. Now you are asked how much will be the induced EMF. So in the complete loop, if I talk about, it will be 0. Okay, you will move in the complete loop, it will become 0. But here B is not constant everywhere. It is changing. How? B naught X by A. X is changing, B is changing. The loop is moved with a constant velocity V naught I cap, means towards the right we are moving. The induced EMF is. One thing is, I can find induced EMF by d phi by dt, or I can use the motional concepts. That way also I can write. Let us do first with motional concepts. At a particular instant, let us take the loop is somewhat here. I don't know where it is at that instant when I'm finding it. It is somewhat here at a distance. Let us take X from here. At a distance X from here. Now I'm writing the induced EMF one by one for all the 4 conductors. Let me name it A, B, C, D. For BC, if I write, you see this BC is at distance x plus d from here, okay, and there if I write, it is moving towards the right with velocity v. So v cross b, b is outside the plane, so v cross b. So lower is positive, upper is negative. V cross b, and how much is the induced EMF here? B is B naught into x by A. How much is x? X plus d. This is my B into V into L into V into L is d. Okay, this is my induced EMF in this BC. This is I am saying EBC. Let me write it, EBC. Okay. Now let us write for DA. I am showing the polarity here. Okay, don't see EBC means EB minus EC. No, I am showing this polarity here, and I am just writing the magnitude there. I'm showing the polarity here. So it is moving with velocity v in this direction. Magnetic field is B naught x by A. Okay, so V, okay, towards the right, cross B. So lower will be positive, upper will be negative. And how much is that? B is B naught x by A into V into the length is d. Now if you talk about AB and CD, AB and CD, they are parallel conductors. Okay, they are parallel conductors, and they are, you can say, my magnetic field is changing along x. So whatever be the induced EMF in this, the same induced EMF will be in this. But one more thing, I am saying V cross B, velocity is towards the right. When I do V cross B dot dl, that will become 0, because V cross B is coming perpendicular to the length. Anyway, it is coming 0 only. So here I will say EAB is 0 and EDC is 0. Not cancelling, they are 0, just 0. Got it? Now in the complete loop I have to find. So when I move in the complete loop, so this plus and then this drop. So one I'll take as positive, another as negative. You subtract these two. Okay, so how much it will become? This will become B naught into x plus d by A into Vd minus this B naught x by A into Vd, and B naught x by A into Vd will get cancelled. So this will become B naught into Vd square by A. B naught into Vd square by A. A option. Another way to do this was find the flux through this at any x. Okay, shall I do that? Let us do this. My B is somewhat here, my loop is somewhat here at a distance x from here. Let me take this something different. Let me take this distance as A at a particular instant. Okay, and from here at a distance x, I'm taking a small thin strip. Write the flux through this thin strip. What that will be? There B, which is B naught x by A, into the area of this. Area of this is dx. This thickness is dx into d. So d into dx. This is the flux through this strip. Integrate it, and my x goes from A to A plus d. This will become my flux phi. Differentiate phi, you'll get the same answer. And dx by dt is my v that you need to put. When you will differentiate it, you'll have dx by dt, that will become my v. So you solve it, you'll get the same answer both the ways. So two ways to do this. This was asked in 2021. Okay. Another question. In a conducting bar of length L, Okay, a conducting bar of length L is free to slide on two parallel conducting rails as shown. This bar is free to slide. Two resistors R1 and R2 are connected across the ends of the rails R1 and R2. There is a uniform magnetic field B pointing into the page. Okay. An external agent pulls the bar to left with a constant speed V. The correct statement about the direction of induced currents I1, I2 flowing through R1 and R is R1 and R2. Okay. So we need to find which one is clockwise, which one is anti-clockwise. So two ways to do this. You can replace this with a effective battery. So V towards the left. Okay, it is towards the left. Yeah. So V cross B, lower is positive, upper is negative. Lower is positive, upper is negative. So a battery will come somewhat like this. Are you able to see this? Not clear? Let me use different color here. So lower is positive, upper is negative, like this. So when you do like this, the direction of current is here, this, okay. Through R1 it is clockwise and through R2 it is anti-clockwise. This is one way. Second way, from the two loops, see, the flux through this loop is decreasing. If it is decreasing, it will try to, the flux that is inside, the flux inside is decreasing, so it will induce its current inside only. It will induce its current in such a way that the field will be inside only, okay, therefore clockwise. Through this, the flux that is inside is increasing, so it will apply its outside, so therefore it is anti-clockwise. So through R1 clockwise, through R2 anti-clockwise. Through R1, so I'll say I1 is clockwise, I2 is anti-clockwise. I1 is clockwise, I2 is anti-clockwise. Clear? Okay. Now motional EMF due to rotational motion of conductor. We are having here a conductor and it is hinged about this point. We are rotating it like this with some angular velocity omega. Will there be induced EMF? Yes, because if you see small sections, they are moving with some particular velocity. So you can say induced, each section will have some induced EMF and you integrate to find the total induced EMF, you will get the induced EMF in this rod. Okay, so what I am doing is, at a distance x from here, I am taking a small section having thickness dx. This dx thickness is moving in this direction with velocity v. How much is this velocity v? I'll say this velocity is omega into x, because v is equals to r omega. Here r is my x. Omega into x. Okay, so how much is the induced EMF in that dx section? So you'll say dE is v cross b. So v cross b. V cross b. This is positive, this is negative. Getting it? V cross b dot dl. So, and how much is that value? V is omega x. B I am saying is uniform. Let us take B there. Okay. B I am considering as uniform. So V cross B dot L, and L is my dx. Is this right? And just you integrate it. X goes from 0 to L. This will become B omega. Integration of x will become x square by 2. Limit will go from 0 to L. And this becomes B omega L square by 2. Important formula to remember. Let us highlight it. Okay. B omega L square by 2. How we got the polarity here? For any section you consider, okay, you do V cross B. Okay, so this is coming positive, another is negative. So overall, when effectively I'll see this will be positive, this end will be negative. Okay, when I'll sum for all the EMFs, effectively I can say this end comes to be positive, that end comes out to be negative. Okay. Now let us do a question on this. This question was asked in April shift 2014. Okay. No, there used to be one shift only. So April 2014. A rod of length 60 centimeter rotates with a uniform angular velocity 20 radian per second about its perpendicular bisector in a uniform magnetic field 0.5. The direction of magnetic field is perpendicular to the axis of rotation. The potential difference across the two ends of the rod is simple. You can just use the formula B omega L square by 2 and you can put the values and you'll get the answer. Is that correct? No. That will become incorrect. Here you need to understand this question properly. What it is mentioning here. He is saying that, just a minute. Yeah. So in the question it is mentioned that this is the rod and this is rotated about perpendicular bisector. Let us take, this is my perpendicular bisector and it is rotated like this. Perpendicular bisector in a uniform magnetic field, the direction of magnetic field is parallel to the axis. Means I am taking my axis like this, so magnetic field is also like this. You may consider inside the plane or outside the plane. Now the potential difference between the two ends, between this end and between this end, and that will be 0. How? If you find the potential difference across this, what that will be? B omega into this length square by 2, and same potential difference across this, B omega into this length square by 2. Okay. And if you see the polarity, V, let us take, I am rotating like this. So V cross B dot L, this is positive, this is negative. Same, when I do here, it is moving like this. So V cross B dot L, so this is positive, this is negative. If you see the polarity of this and this is coming out to be the same. So the potential difference across this end and this end is 0. Getting it? With respect to the center, both the ends are having same polarity and the same magnitude of EMF. So between the two ends, the potential will be 0. This point is clear? Yes. Sometimes it happens like we are in a flow and we just see, oh, this is the question. Okay, B omega L square by 2. Immediately we remember the answer, we remember the formula, put the values, omega is this, L is this, B is this, and you got the answer, you mark the answer, that becomes incorrect. Induced electric field. Now let us talk about induced electric field. So in a region where the magnetic field is changing with time, let us take, here I am saying the magnetic field is there inside the plane. And my magnetic field B, this is changing with time. If I make a loop and I ask you, will there be induced EMF? You will say yes, there will be induced EMF because the flux is changing through the loop. The induced EMF will come through the loop, isn't it? Yes, that is correct. The induced EMF will be there in the loop. Will there be induced electric field? Yes, in the loop, if you talk about the induced EMF is there, it means there will be induced EMF also, induced electric field also inside that. But in free space also, yes, that will be there. In free space or inside a conductor, whether you put, you can say some loop there or some conductor there, there will be induced EMF in that. Or if nothing is there, the induced electric field lines will be there. So what I am doing is, if I take, let us take this as a loop. I considered this as a loop. Okay. Through this loop, if I write the change in the, what is the flux? First of all, let me write what is the flux. It will say the flux is B dot A. They are in the same direction. So B into area. Area, this radius is R. You may write area is pi R square. So just this will become B into pi r square. The flux is changing, the field is changing with time. So I'll say the induced EMF, what is that? Minus of d phi by dt. So I'll say that is minus d by dt of b into pi r square, or you can just write b into a. B into a. B is changing with time, area is constant. Let us take a out. This is my induced EMF, and this induced EMF might have come when we have a loop, okay, but when you, let us take, you move in a hypothetical loop also, there will be induced EMF in that also, okay. So I'll say basically there are induced electric field lines, okay, there are induced electric field lines. So if I say in this loop electric field lines will come, okay, I'll say in this loop, I'll say that like there will be induced electric field lines, okay, that we say as my induced electric field. And how that will be? So let us take, if induced electric field is E, so integration of my E dot dr is the magnitude of that will be my induced EMF, okay. So in this loop, if I write that integration of E dot dl in the complete loop, in this closed loop, okay, that will be equal to my magnitude of induced EMF. I'm just taking the magnitude. So this will come out to be integration of E dot dl is equals to minus of, what is area? Area I can put as pi r square there into dB by dt. This okay, I'm using capital R, let us write it capital R here, capital R here, okay. So what is integration of E dot dl? So that will become E into integration of total circumference, that is 2 pi r, so E into 2 pi r, just writing the magnitude, I'm not taking the sign there, I'm just writing the magnitude. E into 2 pi r will become pi r square into dB by dt, okay. So from here r got cancelled, pi got cancelled, E becomes equal to r by 2 into dB by dt. If B is changing with time, there will be induced electric field. This is my induced electric field. Okay. Here I'm considering the magnetic field lines to be inside, okay. So when I say let us take dB by dt is positive, I'm just want to write the directions of the field lines, okay. Let us take my dB by dt is positive, field is increasing inside the plane. So how much you can say, if there is a loop, how the current would be there? The current would be outside like this, okay. If there is a loop, the current would be outside like this. It means the electric field would be like this. The electric field would be like this. So I'm considering my dB by dt to be positive if that is inside, okay. So it induced electric field lines will be outside. Not only one, like this. These will be my induced electric field lines. Induced electric field questions are not asked in mains. I'm telling this for conceptual clarity, okay. It's not asked in mains. So induced electric field lines will be like this. Here you see the field lines are making closed loop, but we have we read that electrostatic field lines never form closed loop. Here they are closed loop by electric field lines. Yes, there we discussed that the electrostatic field is never in closed loop. That was electrostatic field. Here that is not a static condition, okay. This is not a electrostatic field. This is my induced electric field, okay. Static field is due to static charges, okay. It is not due to that. So this is my induced electric field and it is in closed loop. It makes closed loop. And if you move in a closed loop, you see, if you move in a closed loop, that is equal to the total induced EMF in that loop complete. Okay, so here my induced electric field forms closed loop. It forms closed loop. Okay, so I'm not going into much detail of this because that is not required. I was just explaining all the things such that if some conceptual question is there, you can answer it. But in mains, questions are not asked from this. Okay, eddy currents. Let us take, you are having a metal surface and there you are changing the field through it or flux through it. Let us take, you are changing the flux through it. What happens? Now metal surface is there. On the metal surface, you can say metal is there, it means electrons are there. Okay, so electrons inside the surface only, they will form some closed loop and they will move in that closed loop to such that the induced current opposes the change, and these induced current we say eddy currents. Okay, so here eddy currents will be there to oppose the change of the flux. Here I am having this coil, current is passing through the coil, due to which the flux is there. I am changing the current, the flux is changing, the flux is changing. So there will be some closed loop formed by the electrons and there will be some induced currents, and that induced currents will try to oppose the change of the magnetic field or of the magnetic flux through that. And these currents we call them as the eddy currents. And these eddy currents actually heat up the material. A metal sheet is there, inside the sheet only the current is moving. Okay, inside the sheet small loops will be formed. Okay, the current is moving in that loop. So what will happen? The metal will get heat up too much. Okay, so in transformer and in our motor, so eddy current losses are there and we try to reduce that. There are certain methods, we need not go into the details of that as of now. Okay, such that the closed loop is not formed, we make such things, you use laminations. Okay, closed loop will not be formed so that eddy currents will not be there, but that is not required as of now. So just need to understand what is eddy current. Got it? Okay, now self-inductance. Let us take a coil is there. We discussed till now external magnetic field is there, okay, due to which the flux will be there through the coil, and if that flux changes, there will be induced EMF in the coil. But what if I change, so let me again make that statement, but what about the flux due to the coil itself? Yeah, that is a proper line. So what about the flux due to the coil itself? Coil is there, it is having its own magnetic field, some current is there, let us take. That own magnetic field will have some flux linked through it. Okay, so when that flux changes, due to that also there should be induced EMF. Yes, due to that also there is some induced EMF. Getting it? If you are not clear with my point, let me discuss. Let us take, this is a coil, or make it other way, multiple loops. Okay, and let us take, I have connected some battery through this coil like this. Some current is there in the coil. Need not show the source as of now. Need not show the source as of now. Let us take some current is there in the loop. Due to this current, also there will be a linked flux through this coil. And let us take that flux linked is phi. If that phi changes, will there be induced EMF? Yes, there will be induced EMF due to that. Okay, so that linked flux is phi, and that linked flux will be there. If we write that in terms of its magnetic field, okay, and current, you can write. So that phi, whatever be that phi will be proportional to the magnetic field. Okay, what is the magnetic field produced due to it, and this magnetic field is basically proportional to the current because that field is due to the current. So I'll say this my phi is proportional to the current of the coil. And if there are n turns, I can multiply this with n. So my total flux, that is n phi, is basically proportional to the current of this coil. This is self flux. Okay, this is self flux, not due to external. This is my self flux. I'll write it as self flux. Okay, so the total flux will be proportional to the current, and the proportionality here is known as the self-inductance of the coil, or I call this L as coefficient of self-inductance. Getting it? Here the induced EMF is coming due to the change of the flux, and that flux is due to its own current. Okay, so this L I can say is basically N into phi by I. This L we call as the self-inductance. And what is the unit of this self-inductance? We'll come to that. Now if I differentiate it, let us differentiate it. N d phi by dt with respect to time, L di by dt, add a negative sign. What is this? This is the induced EMF. Okay, so this EMF becomes minus L di by dt. And from here, if I see the units, E is volt, time is second, so this is volt second per ampere. Okay, the unit of this, the SI unit of L, if I write, this becomes my volt second per ampere. This is volt second per ampere, and this 1 volt second per ampere, we call this as my 1 Henry. We denote that with H. Henry. Okay, so the unit of inductance is Henry, or we say unit of self-inductance is Henry, that we denote with H. Okay, and also we got the EMF that will be induced across this inductor, and we call that as the back EMF. We'll come to that again. Now let us try to find the self-inductance of a solenoid. So what we will do, the steps are: find the flux and put that flux is equals to Li, and L will become my self-inductance. Okay, this is my solenoid. Let us take the length of the solenoid is L, N, small n, this is number of turns per unit length. Current I is going. What will be the magnetic field inside the solenoid? I am considering this to be long solenoid. I'm considering this to be a long solenoid. It means B is constant inside. And what is the formula for that? Mu naught Ni. Remember this? We derived this. This formula is important. Mu naught Ni. So B is mu naught Ni. Due to this B, if I find flux through one coil means one circular loop here. Okay. What will be that? B into A. So mu naught Ni into area. Mu naught Ni into area. Okay, this becomes my flux through the one loop. I need to find the total flux, multiply with number of turns, total number of turns. Total number of turns is turns per unit length into the length. Turns per unit length into the length, isn't it? Yeah. So this will become mu naught N square, mu naught N square into I into A into L. This becomes my total phi, and I'll put this phi equal to L into I. This I got cancelled. Self-inductance comes out to be mu naught N square A into L. You see this one thing, self-inductance is not depending upon the current. Self-inductance depends upon the number of turns there, the area of the coil there, okay, area of the whatever the loop is there, the length of the coil, means the dimensions and all those things, but it is not depending upon the applied current. Getting it? This is just like resistance. So L I got, this is my inductance of this coil, and if I write A into L as volume, I'll get inductance per unit volume. So if I write L divided by AL, AL is my volume, so this is my mu naught N square. This is my inductance, or I'll say self-inductance per unit volume. Self-inductance per unit volume for a solenoid, not general formula, this is for a solenoid. Area, how you can write, if radius is given, you can put area as pi r square. Do you need to remember this formula? If you can, well, if you cannot, just quickly derive it. Okay, let us do the same exercise for a toroid. I'm having a toroid here, and I have cut this so that you can see the cross section of this toroid, and we need to find the mutual inductance. How to find that? Sorry, self-inductance. How to find that? Again, the same exercise. We'll find total flux phi, and then we'll put that phi is equal to Li, total flux phi. So through one of the cross section, that is this. Let me draw it. Through one of the cross section, that is this. Let us find how much is the magnetic flux. So what I did, this is the center line at a distance x. At a distance x, or we are using r here, okay. At a distance r, I am taking a thin strip. This is my thin strip. Its thickness is dr. I am writing the flux d phi. So d phi, there will be magnetic field there into the area dA. What is dA? dA will be, this height is h, this width is dr, so h dr. So h dr. What is B? How to find B? You know the formula. What you can do is, to find the B at a distance, you can use Ampere circuital law. Okay, I'm moving in a complete circular loop. I'm moving in a complete circular loop like this of radius r. In that circular loop, I'll say integration of B dot dl is equals to mu naught into I enclosed. I enclosed will be I into the total number of turns. Total number of turns n. Here I am considering the capital N as number of turns total. Okay. So B dot dl integration will become B into 2 pi r is equals to mu naught Ni. So B becomes mu naught Ni by 2 pi r. Put it there. So d phi is equals to B, which is mu naught Ni by 2 pi r into h dr integrated. What is my constant here? Everything else is constant other than r. Okay, so everything else I'll take out, and r changes from r1 to r2. The inner radius is r1, outer radius is r2, so r1 to r2. What it is now? So mu naught NIH divided by 2 pi, that was constant. Integration 1 by r is ln r, limit r1 to r2, so this will become ln r2 by r1. This is flux through 1. Total flux multiply with number of turns. Number of turns is n. So n into phi. This is my phi. What I'll do? N into phi, that is equal to Li. So n into phi So n into this, it will become square of n mu naught n square IH by 2 pi ln R2 by R1. Okay, is it clear? And this is equal to my L into I got cancelled. This becomes my self-inductance for a toroid. Do you need to remember this formula? Not at all. Don't remember this. Just try to understand how we are doing, how we are deriving it. Okay, coming to some questions on self-inductance. This is 2019 question. A copper wire is wound on a wooden frame whose shape is that of an equilateral triangle. Now equilateral triangle wooden frame is there. Okay, you may consider like some shape like this, equilateral triangle. Of linear dimension, each side of the frame is increased by, okay, if the linear dimension each side of the frame is increased by 3, keeping number of turns of the coil per unit length of the frame is same, the self-inductance of the coil is. Okay, so here some self-inductance will come, and somewhat similar to the solenoid, instead of circular loops, there will be triangular loops. Okay, but the thing is, here area will change, otherwise the self-inductance formula will remain the same. So what it will be? Mu naught n square AL. So self-inductance is mu naught n square AL. So what they are saying is, L is increased 3 times, keeping the number of turns per unit length frame to be constant. Now this n is constant, this is constant, and your side is increased, it means area will be increased, yes, and this length L is also there, total length of the solenoid, that will also change, because when you are making the loops, total number of turns was there, let us take some. Now I increase the dimension, number of turns is same, but the length of the wire is also limited, means the same. So total length of the wire is same. So when you will be wounding that, what it will become, if the dimension is 3 times, the total length will become 1 by 3 on which it will be wound. Are you able to understand? I am having a wire of length L, I am wounding it on this wooden. Okay, now what I did, I increased the dimension of this wooden frame by 3 times. So your number of turns that you will wound, that will become 1/3. Total number of turns per unit length is same, but total number of turns will become 1/3. It means your length on which it will be wound will become 1/3. So this become 1/3, and this becomes, because area is side square, proportional to side square, so it will become 9 times. So L dash will effectively become 3 times. So increase by a factor of 3. See, it will increase by a factor of 3. Is this point clear? Now you may see, sir, here it is a triangular thing, and do we need to derive? No, just if you understand the concept of solenoid, you can quickly do this question. There is no confusion at all. Now back EMF developed in the inductors. So as I mentioned phi, that was equals to Li, and when I differentiated minus d phi by dt, this will be L minus, sign is there, minus L di by dt. So this becomes my back EMF, that is minus L di by dt. So if an inductor is there, let us take, how we show an inductor? Show like this. Let us take the current is like this. If your di by dt positive, this will be plus, there is a drop. If di by dt is positive, it is minus L di by dt, magnitude of that. So this will be a drop, minus plus. If di by dt is positive. And if di by dt is negative, the polarity will become opposite. Okay, minus plus if di by dt is negative. Okay, so we say when we are moving in a loop in direction of current, there is a drop. How much drop? LdI by dt drop. So we say minus LdI by dt. We are moving in direction of current through inductor. Okay, there will be a drop of LdI by dt. If di by dt positive or negative, you can consider accordingly. Okay, some questions. The current in inductor is given by this, where t is time in second. The magnitude of induced EMF produced in the inductor is 12 millivolt. The self-inductance of the inductor is, okay. So when we are saying we need to find self-inductance, the current is given to me, the induced EMF is given to me. How I can relate? Induced EMF is minus LdI by dt. This formula, no, I know. Induced EMF is 12 millivolt. So this is 12 millivolt. This is minus L d by dt of I. Anything else? No. Okay. So from here I can differentiate it, and also here it is just telling the magnitude of the induced EMF, not the polarity. So need not consider the negative sign. Just he is saying the magnitude. He is talking about the magnitude. Okay. Now differentiation of 3t plus 8 will be 3. Just 3 is constant, that will come out. Differentiation of t is 1. Differentiation of 8 is 0. So it will become just 3. So 3L is 12 into 10 to the power minus 3. So L comes out to be 4 into 10 to the power minus 3, or I will say 4 millihenry. 4 millihenry. Easy? Yeah. Such questions are also very much asked in mains, and these questions are very, very simple. Okay, as per the given figure, if di by dt, okay, he is talking about di by dt is minus 1 ampere per second, what does it mean? It is decreasing. But don't worry about this, that thing. Di by dt is, he is saying you can use it directly there. Then the value of AB, VAB at this instant will be, VAB means VA minus VB. So what I am doing is, I am starting from point A, moving in this direction, I'll go to point B. Okay, starting from point A. So potential is VA. Now across the resistor in direction of current, potential will drop, minus IR. So minus 12 into 2. Then in the direction of current through an inductor, minus LdI by dt. So minus L is, okay, let me write it properly so that you are not confused. Let me write it just minus LdI by dt. Okay, I'll come back by putting the values again. Okay, now I am going from positive to negative again. There is a drop, so minus 12. Minus 12. I reached point B, so this is my VB. Now put the values. So VA minus 24 minus, what is L? L is 6. What is di by dt? Minus 1. Minus 1. Minus 12. This is VB. So minus 6 minus 1 is plus 6. Okay. So this is VA minus of 24 plus 6 minus 12. So this is minus 30. This is VB. So VA minus VB, which is VAB, that comes out to be 30 volt. These type of questions are very much asked in mains. Make sure you are clear with this and not confused with the polarity. If you are confused with the polarity, again try to do this question. So when we are moving in direction of current, just write minus LdI by dt. Okay. Energy stored in an inductor. Now inductor, some current is there now. It means some current is there, it means there is some magnetic field inside the inductor. If some magnetic field is there inside the inductor, it means there is some energy that is stored inside the inductor. Okay, field is there inside means there is some energy that is stored inside the inductor. Okay, now this was the inductor. Initially current was 0. Now slowly the current was increased, and the current now is some, let us take I current. What I will do is I will find how much work I did or how much work was done by the battery or external source in making the current from 0 to I, and that will be equal to my energy that is stored, because there is no loss. If the resistance is there, there will be loss. Inductor will not make any loss. Getting it? Okay. So at any instant, let us take current is I. Okay. So at any instant current is I. How much is the potential? At any instant, if you talk about the potential, that is minus L di by dt. So if you talk about the magnitude of the potential across the inductor, that is L di by dt. How much is the power at a particular instant? So power is equal, so this becomes my potential. Let me write this as V. Okay, so power is V into I, so L into I into di by dt. Okay, how much energy that is given to the inductor? V dt. Power, integrate power dt, that much amount of energy I'm giving. So integration of it will become Li di, L is constant, that will come out. Integration of I square by 2, 0 to I is the limit, so it will become half Li square. So the energy stored in the inductor, that becomes half Li square. If the current is I, the energy stored in the inductor is half Li square. If let us take current changes from I1 to I2 and you are told how much energy is supplied, you can do half Li I2 square minus half Li I1 square. Final energy total minus initial energy total. Clear? Okay, good. Now let us try to find the energy density. So we discussed that if the inductor is there like this, current is I, so the energy is half Li square. Let us take, this is my solenoid. What is the inductance of the solenoid? Mu naught N square Al. This is the inductance of the solenoid. Let us put it here. So half L is mu naught N square Al into I square. What is mu naught Ni? As B. Multiply and divide with mu naught. Mu naught Ni as B. So this becomes B square. So B square by 2 mu naught into A into L. What is A into L? Volume. Energy divided by volume comes out to be B square by 2 mu naught, and this we call as my energy density, which we denote with small u. So this becomes my energy density, that is B square by 2 mu naught. In electric field we discussed the energy was half epsilon naught E square, the energy density of electric field. Half epsilon naught E square, energy density of electric field. Energy density of magnetic field is B square by 2 mu naught. Keep these two formulas in mind. Okay, these two formulas are important, and in electromagnetic waves we'll come back to them. So B square by 2 mu naught is the energy density of magnetic field. I am writing for electric field again here. For electric field, it was half epsilon naught E square. Here it is B square by 2 mu naught. You see that similarity is there? Yeah. Half. This is 1 by mu naught. This is epsilon naught. If you see the positioning of epsilon naught and mu naught in the formulas of electric field and magnetic field, electric field epsilon naught comes in denominator, magnetic field mu naught comes in numerator. Therefore, it is here, this is in numerator, it is in denominator. okay, and B square, there E square. From similarity you can remember this formula. Now coming to some questions on this, let us discuss. The current in a coil of self-inductance 2 Henry is increasing according to I, that is 2 sine t square. The amount of energy spent during the period when current changes from 0 to 2 ampere. How much energy will spend? The energy that is changed in the my inductor. How much was the initial energy? Half Li square. How much final energy? Half I final square. So the amount of energy spent, I'll say that is equal to the change in the energy, half L I final square minus I initial square. What is I? I is 2. What is I final? I final is 2 ampere, so 2 square is 4. Minus what is I initial? It was initially 0, so 0 square is 0. This comes out to be 4 joules. Is this clear? 4 joules. Just see how much the current changed, and directly we are able to write how much energy is changed. Okay, the self-produced EMF of a coil is 25 volts. When the current in it is changed at uniform rate from 10 ampere to 25 ampere in 1 second, the change in energy stored of the inductance is how much energy change? Current is changing from 10 to 25. How much energy is changed? Half L I final square minus I initial square. This is what I will write. Okay, what is I? I is I know I final, I initial. What is L? L is not given directly. It is saying self-inductance, the self-produced EMF is 25 volts. So EMF, we know that is minus L di by dt. You know this thing? What is this? This is 25. So 25 is equals to minus L. What is di? Change di by dt. It is uniformly changed, so I can write this as delta I by delta t. Delta I by delta t. Okay, so this is 25 is equals to minus L into what is delta I? Delta I is my 15. Final is 25, initial is 10. So delta I is 15. What is delta T? Delta T is 1 second. Oh, yeah, 1. Negative sign is there. What to do? He's telling about the magnitude. So just neglect this negative sign. He's telling about the magnitude. Now from here, L comes out to be 25 by 15, which is 5 by 3. L is 5 by 3, let us put it here. Half L, which is 5 by 3, I final, which is 25 square, 625, minus 10 square is 100. So this becomes 5 by 2 into 3 into, this is 525. Is it divisible by 3? Yes, it is. So 3 into 1 into 7 into 5, 175. Is it perfect? Yeah, 175. 175 into 5 will be 200 into 5 is 1000 minus 125. 875 by 2. That will become 437.5 joules. Yeah, 437.5 joules. Okay, getting it? If you are having any doubt while you are watching this video, make sure you put your question in comments and we will come back to you. We will take your question. Okay. Now let us discuss about a series combination of inductor. Let us take, we are having two inductors having that's L1, having inductance L2. This is L1, this is L2. Some current I is passing, and effectively it is my L effective, or I can say L series, LS. Current I is passing. If I write the total EMF across this, what I'll say, this is minus L1 di by dt minus, this was L1, not Li, this was L1. So minus L1 di by dt minus L2 di by dt, and this becomes my effective L there. So minus L series di by dt got cancelled, and I got L series comes out to be L1 plus L2, just like a series combination formula of a resistance. If two resistance are in series, we used to say effective resistance will be R1 plus R2, or 3 is there, R1 plus R2 plus R3. Same thing with the inductors, L1 plus L2 plus L3, like that. Now for parallel combination, this is one inductor, this is another, some current I is coming, this is I1, this is I2, this is L1, this is L2. Effectively, I made it like a single inductor. Total current is I, inductance is L parallel. Okay. So for this I say I is equals to my I1 plus I2, differentiate it, di by dt is equals to di1 by dt plus di2 by dt. We know what is EMF or potential. If I write V is equals to minus L di by dt. Okay, so if I write di by dt, that will become minus V by L. Okay, so when I say di by dt, I'll say this is minus V divided by L parallel. This is minus V divided by L1 minus V divided by L2. From here, I got 1 by L parallel comes out to be 1 by L1 plus 1 by L2. Okay, the parallel combination formula is same as that for the resistors. We used to have 1 by R1 is R parallel is equals to 1 by R1 plus 1 by R2, same thing. Okay, capacitor is opposite, so keep this in mind. For inductors and resistors, formulas are same. For capacitor, it is opposite. Series becomes parallel, parallel becomes series effectively. Okay. Okay, so let us have a question on this. Let us draw some inductors. Okay, so this is 1 Henry, or let us take this is my 6 Henry, this is 3 Henry, this is let us take this is 2 Henry, and one more here. Yeah, and this is let us take 4 Henry. Is this fine? Yeah. So the question is find effective my total inductance. Let me write the other way. Find total inductance. Here we are not talking about the mutual coupling and all those things. There is no mutual inductance here in this particular case. We will talk about mutual inductance in a while. Now here if you see these 6 and 3 are in parallel. So what will be the effective of this? 6 into 3 divided by 6 plus 3. What is that? 2. 6 into 3 divided by 6 plus 3. This is 2. And this 2 into this 2 is in series. So total is 4. This 4 and this 4 is in parallel. So the effective will be 2. Getting it? So here my answer comes out to be 2 Henry. L effective. L effective questions are not there, but still may ask, maybe asked in mains, because these are easy things. Now current distribution in parallel combination. So let us take some condition is there and some circuit is there, okay. So L1 and L2 two are in parallel and some at steady state, let us take some current I1 and I2 is flowing. So what is I1? What is the relation between I1 and I2? Now I'll say the potential drop is same, okay. So across this inductor and across this inductor potential drop is same. So I'll say L1 into di1 by dt is same as L2 into di2 by dt because potential is same. It means L1 di1 is equals to L2 di2. I'm considering total, initially the currents were 0, both the currents were 0 and they were going from 0 to I1, 0 to I2, okay. So L1 I1 is coming out to be L2 I2. So if you want to find the ratio of the currents or if you want to relate the current, you can relate it like this. L1 I1 will be equal to my L2 I2. Now talking about mutual inductance. Now let us take, we are having two coils. Due to one coil, there will be some flux linked in the other coil, okay. Now if I change current in this coil, the flux through the coil will change, yes, and due to that changing flux there will be induced EMF, yes, there will be induced EMF. So when I am saying this is my coil 1, this is my coil 2, due to this coil there will be some flux through this coil. How much that? Flux on coil 2 due to 1. The number of turns of coil 2 I am considering as N2, so total flux becomes N2. And this will be proportional to the current of coil 1 because, why proportional? Because it is due to the field of coil 1 and that field of coil 1 is proportional to the current of coil 1. So this is proportional to current of coil 1 and the same way this proportionality constant is my mutual inductance. What should I write? Mutual inductance of coil 2 due to 1. Now the important thing is either you find mutual inductance of coil 2 due to 1 or you find the mutual inductance of coil 1 due to 2. Both are same. So we just write M only. So whenever we write, we just write M because both are same. So I'll say this N2 phi to 1 is my mutual inductance M into I1. You can, other way you can do, you can, due to current in this coil, you can find the flux due to on the other coil, okay. So what that will become total flux? That will become number of turns in coil 1 into flux of coil 1 due to current in coil 2 and this will be mutual inductance into current of coil 2. The current will be of that coil due to which you are considering the field there or the flux there, due to which you are considering, okay. Due to the presence of field of this, I am considering the flux through this, therefore here the current is I1. When I am considering due to that, the current will be I2. But anyways, I am saying M12 is same as M21, okay, the same thing. We will do a question on this and you will see that actually it comes out to be same, okay. So yeah, we discussed that M12 is same as M21. Now here we are having two coaxial solenoids, okay. Inner one is having radius R1, outer one is having radius R2, total length is L, number of turns of inner one is N1, outer one is N2. So let us do one by one. What I will do, first let me find M12. Mutual inductance of coil 1 due to coil 2. So what I will do, I will find phi 12. Flux in coil 1 due to coil 2. Due to coil 2, there will be magnetic field whole throughout this. And how much that due to coil 2, yeah, mu naught, number of turns per unit length of 2 into I2. This is my B2. So flux will be my B2 into the area of coil 1, because I need to find flux through 1 only, na? Area of coil 1 into number of turns of coil 1. Is this clear? Yeah. Okay. So this is B2 into area of coil 1 into the number of total number of turns. This becomes my total flux. Okay. So or sometimes we write as from 1 turns into n. You can do anyways. This same thing. So this is my B2. B2 is mu naught n2 I2. Mu naught n2 I2 into A1 into N1. Clear? Any confusion in this? Okay. So 512 is like this. Now this 512 I'll write as what? I'll write as M12 into I2. So M12 into my I2 is equals to mu naught N2 I2 A1 N1. I2 got cancelled. This is mu naught N2 and A1 into N1. N2 is total number of turns. This is turns per unit length. Okay, turns per unit length, or you can write as N1 as number of turns per unit length, small n1 into N2. So this will become mu naught N2 A1 into N1 into L. Total number of turns is turns per unit length into length. Therefore, I wrote N1 as number of turns per unit length into length. What it is now? Mu naught N2 N1 A into L. Okay. Now let us do the same thing other way. Same thing other way. Same thing other way means I am passing current through the inner one, due to which the magnetic field will be there only inside. Only inside region only the magnetic field will be there. How much that will be? That is my B1 and that is mu naught N1 I1. Due to this, the flux will be there through the bigger coil. How much that will be? Into the area of only the inside one only I will take, because in this there is no magnetic field. When you are finding the flux through the bigger coil, the flux will be there only in the inner area only. So I'll just take the A1 only. Okay, this A1 only I'll take. So when I say phi, this will become mu naught N1 I1. This is N1 into I1. Okay, I1 into my A1 area into the number of turns of which the inner one N1. This becomes my total flux. This total flux I'll write as mu into N. Okay, sorry. Total flux I'll write as M into M21 into I1. So M21 into I1 is equals to mu naught N1 I1 A1 N1. I1 got cancelled. So M21 comes out to be mu naught N1, capital N1. Sorry, I did a mistake. This should be N2. This should be N2 because I am finding the flux through the outer one. Na? So total number of turns I take N2. This should be N2. And N2 I can write as total turns will be number of turns per unit length into length. So number of turns per unit length into the length L. And you see from here M21 is same as M12. Mu naught N1 N2 AL, mu naught N1 N2 AL. So this comes out to be correct. So when in questions some two loops will be there and you will be asked find the mutual inductance. So which one is easy for you to find that. let us take, it is easy to find mutual inductance of 2 due to 1, do that, or mutual inductance of 1 due to 2 is easy, do that. Other may take longer time, but the value comes out to be same. So sometime 2 coils are there in the question, it will be given find the mutual inductance of the inner coil due to the outer one, or find the mutual inductance of the outer coil due to the inner one. The answer will be same. Answer will be same. Getting it? Okay. Coupling coefficient. So the coupling coefficient is K. Okay, and this K, the mutual coupling coefficient is the mutual inductance M divided by root of self-inductance of first coil into self-inductance of second coil. If two coils are perfectly coupled, this mutual coupling coefficient comes out to be 1 if it is perfectly coupled. So for perfect coupling, my K will come out to be 1. Perfect coupling means no leakage of flux. Whatever you can say field lines are produced by one coil, all the field lines are passing through the second coil. If this is the condition, we will say perfect coupling is there. No leakage. Leakage means, let us take, you are producing here 50 field lines. I am considering 50 field lines, okay. So, and half of the field lines are going out, 25 are passing, let us take. So, it is not a perfect coupling. Getting it? Perfect coupling means whatever is the field, the same field is passing through the other coil. Perfect coupling is there. Otherwise, there is some leakage. Okay. So, leakage flux, due to leakage flux, we have losses. Anyways, we will not discuss that thing. Let us discuss now mutual inductance between two coplanar concentric coil. We are having two coplanar concentric coil, one smaller, another bigger, and here B is greater than A, because then only we can find, otherwise it's not easy. Okay, so here some current I am giving on the outer one, and due to which I'll see how much is the flux linked with the inner one, and that flux I'll put as M into I2. Okay, and that way I'll find the mutual inductance. Can we do the other way? Can I pass current through the inner one and then do the same for? You can do, but that will be very difficult. Okay, so better is pass current through the outer one. Okay, find the magnetic field inside. What is the magnetic field at the center of a current carrying coil? Mu naught Ni, sorry, mu naught I by 2R. You know that formula. If I pass current through this, if I ask you what is the magnetic field at the center, so you know the formula, that is mu naught I by 2R. Okay, let us take this current is I2. So it will become mu naught I2 divided by 2 into R is B. This is the magnetic field. Now you will understand this logic why I took this. When I write flux through this, if A is very small, you may consider whole throughout the fluxes or the magnetic field is constant, because A is very small. I will consider the magnetic field at center means magnetic field that is whole throughout the same. So when I write flux, I'll say that will become my B into the area pi into A square. So B mu naught I2 by 2B into pi A square. Getting it? And this I'll write as the mutual inductance into I2. I2 will get cancelled. So I got the mutual inductance M as mu naught pi A square by 2B. Okay. This question is many times asked in mains. Two coplanar coils. Find the mutual inductance. So make sure you understand this concept. Don't memorize the formula. Understand this concept. There may be some turns. If the number of turns are there, you consider those number of turns also, particularly to find the total magnetic field and flux, all those things. Mutual inductance between two coaxial parallel coils. We are having two coaxial parallel coil. One like this, another like this. Okay, let me do like this, small. Let us draw the axis. This is my axis. Let us take this radius is capital R, and this radius is small r, and my capital R is greater than small r. The same logic such that the field whole throughout this region is same. We know the formula of magnetic field due to a current carrying coil which is having current I at a distance, let us take this distance to be some distance x. At a distance x, you know the formula on the axis of a current carrying coil magnetic field? Yes, that is B is equals to mu naught into I into R square divided by 2 R square plus x square to the power 3 by 2. Make sure you remember this formula because this formula is many times asked. Okay, directly also, and many times it is used. So magnetic field on the axis of a current carrying coil is mu naught I R square divided by 2 into R square plus x square to the power 3 by 2. Remember it. Now if I write the flux through this, flux will be the magnetic field there into the area. So mu naught I R square divided by 2 R square plus x square to the power 3 by 2 into, this is B, into pi R square. This is mutual inductance into the current. This current got cancelled. I got the formula for mutual inductance. Don't remember this answer, just understand the concept. Yes, this particular question was asked in my times when I was giving JEE mains paper. So this question was asked. I remember it still. So I was able to solve it because my concepts were clear. Okay, so make sure that you understand it, how I am considering magnetic field due to the current in this coil there, multiply that with area, that becomes my flux, and this flux I am putting as M into I. Okay, now coming to some questions on this. Find the mutual inductance of the arrangement when a small circular loop of wire of radius r is placed inside a large square loop of side L. The loops are coplanar and their center coincide. Okay, we are having a small circular loop and here a large square loop. This assumption will always be there. This assumption will always be there. And if a question is asked in mutual inductance, there are no varieties. There are no varieties. Either they will give two coplanar coils, or they will put the two coils on the axis at some distance, or they will make one square another circle, and they make both the squares. Like these variations are only there. There are not much variations in this. So if a mutual question is coming from mutual inductance, that will be one of these questions only, what we are discussing. Okay. Now find the mutual inductance of arrangement when a small circular loop of wire radius r, okay, the loops are coplanar. Yeah. So what I will do is, this is my current I. Due to this, I'll find, due to this square loop, I'll find the magnetic field at center. I'll consider the magnetic field is constant throughout this circle. Multiply that with the area of this circle, that will become my flux. I'll put that flux as M into I. Okay. So here this is my, let me take this one wire here, from here to here. Due to this, what is the magnetic field at center? What is the formula? You remember it? No? This is my perpendicular. This is my phi 1 45 degree. This is my phi 2 45 degree. So the formula is mu naught I by 4 pi into the perpendicular distance, that is L by 2. This perpendicular distance is L by 2. 4 pi into the perpendicular distance into sine of phi 1 plus sine of phi 2. Sine 45 plus sine 45. This is due to one segment. Multiply this with 4. This will become due to the complete square loop. This is the magnetic field. Multiply that with pi r square. That will become my flux. This is my flux. Okay. And put that flux is equals to M into I. And from there you'll get the mutual inductance. This 4 is getting cancelled. Okay. This is root 2. This 2 will go in the numerator, it will become 2 root 2. So 2 root 2 mu naught pi will also get cancelled. Yeah, 2 root 2 mu naught into r square by L. Everything is fine. I think this is correct. If I missed anything, r square is there. Yeah, mu naught is there. Yeah, this will become 2 root 2 and L will be, yeah, 2 root 2 mu naught r square by L. 2 root 2 mu naught r square by L. C option. Okay, this becomes my mutual inductance. Now here we are having two square loops and we need to find the mutual inductance. Okay, a square loop of wire of side L is placed inside a large square loop of side L. The loops are coplanar and their centers coincide. The value of the mutual inductance. So what you need to do, just the area will change there. Take the bigger one, find the magnetic field due to that at the center, multiply that with the area of the inner one, that becomes my flux phi. Phi is equals to Li, from the phi is equals to Mi, from there you will get the value of M. Okay, so just pause this video, do this exercise and then come back. I hope you are doing it. So pause it and then do it. Okay, you are back after solving. Let us do this exercise quickly. This is the outer one. This is the inner one. This is dotted, all dotted. Got dotted only. No problem. Let us take, this is the current, the magnetic field due to that at center. I'm doing the same exercise again. This length is L. So this perpendicular distance is L by 2. When I write B, that is mu naught I by 4 pi into the perpendicular distance into sine of 45 plus sine of 45, that becomes my root 2. This is due to one side, multiply that with 4. This is due to 4 sides, multiply that with the area of the inner one, that will become due to the, that will become my flux. Put this flux as mutual inductance into I. From there you'll get the mutual inductance. One thing is given, capital L is equals to small l square. So by considering this only, we are able to take this assumption here that this small l is less than capital L. And there is no other option itself. This assumption will be there in the question. Okay, 4 is getting cancelled. Anything else? Yeah, L square is getting cancelled. Anything else? No. So 2 root 2 in the numerator, 2 root 2 mu naught, 2 root 2 into mu naught divided by pi. This only I am getting. And this is given as root x into 10 to the power minus 7. Okay, let us multiply and divide with 4. Mu naught by 4 pi is 10 to the power minus 7. So this will become 8 root 2 into 10 to the power minus 7. So this 8 root 2 is 64 into 2, that is root 128 into 10 to the power minus 7. So I can say this root x is root 128, so x comes out to be 128. X comes out to be 128. Easy questions. No varieties are there. Again I am saying, no varieties are there in mutual inductance questions. Okay. Series combination of inductors considering mutual inductance. Till now we discussed series combination but not considering mutual inductance. Here mutual inductance is there. Now mutual inductance can affect the flux in positive way also, in negative way also. It depends how it is coupled. If you see case 1, let us take here mutual inductance is M. You pass current, so the flux, let us take the current is going like this, so some flux will be there due to the current in L1, okay, that will pass through L2. So that flux is supporting the flux of L2. That flux is supporting the flux of L2, getting it? Yeah. So this flux is supporting the flux of L2. So when I say this is my AB, okay, this is my A and B are outer points. let us take this this as V1 and this as V2. So what is V1? Just writing the magnitude, L1 dI1 by dt. This is due to its own self-inductance plus M into dI2 by dt. This is due to the mutual inductance. Coming back, wait a minute, coming back to the mutual inductance thing. Yeah, we discussed it like this. Now if I differentiate, this is my total flux phi. So we wrote phi is equals to the mutual inductance. Phi is equals to mutual inductance into current. So phi of let me write 1 2 is equals to mutual inductance into the current of 2. So I differentiated d phi 1 2 by dt. This is m into di2 by dt. Negative sign is there here. Minus d phi 1 by dt. What is this? This is the induced EMF in coil 1 due to the current in coil 2. E12. And if I write E21, di1 by dt. Okay. So induced EMF in coil 1 due to current in coil 2. So due to current in coil 2. So m di2 by dt. Induced EMF in coil 2 due to current in coil 1. Current in coil 1. So di1 by dt. Getting it? Okay. Coming back there. Where we were? Yeah. So this is V1. Now why I considered minus here? Oh, sorry, why I considered plus here? Because the mutual inductance, you can say, is supporting the self flux. The mutual flux is supporting the self flux. Okay, the flux due to this on L2 is supporting the self flux of L2. Therefore, plus sign, or other way also I can say, therefore the plus sign. So similarly, I write V2. So I will say this will become L2 into di2 by dt plus sorry, plus m into di1 by dt. Now why I am saying I1 and I2? I is same only. I will say I is equals to I1, that is equals to I2. So everything is same. So L1 plus L2 plus twice of m into di by dt. And this will become my L effective into di by dt. So L effective becomes L1 plus L2 plus 2m. These are positively coupled. Here it is negatively coupled. This current is going like this, so flux will come here, and its self flux is like this. So the flux due to this will oppose the self flux of other. Similarly, the flux due to the other will oppose the self flux of the first. So mutual in this case will be negative. So here if I say L effective, it will become L1 plus L2 minus 2m. So for two series coil, when I say mutual inductance effectors, I will say L1 plus L2 plus minus m, plus minus 2m. Plus and minus depends upon how they are coupled. They are positively coupled, it will be plus. If they are negatively coupled, it will be minus. Okay. A simple question. Two coils, self-inductance L1, L2, series combination. The equivalent inductance of the combination will be positively coupled or negatively coupled. Negatively coupled means D option. No varieties, you see. Okay, growth of current in LR circuit. We are having a LR circuit. There is a resistor, there is an inductor, DC battery is connected. Initially the switch is open. I am closing the switch at t is equals to 0. Cut. Okay, this is closed like this, at t is equals to 0. Now some current will be flowing. Let us take at some instant some current I is flowing like this. Let us write KVL, move in the loop. I am starting from A, moving like this. So it is drop minus IR. So minus IR. Then inductor minus L di by dt. Minus L di by dt. Moving like this. Then battery. I am going from negative to positive. So plus E. So plus E. And this becomes equal to my 0. I moved in the complete loop. So from here I can write my di, and this will come out to be E minus IR there, E plus IR, okay, not plus. I am taking this as towards the right, okay. So LDI will become my E minus IR, E minus IR. LDI by dt. Getting it? So take this in denominator, di is equals to E minus IR, and this is dt by L. Integrate. My current goes from 0 to I. My time goes from 0 to t. This will become ln E minus IR, differentiation of this minus R limit 0 to I. This is t by L. Everything is fine? Yeah. From here I put the limits first. So this will become ln, how should I write properly? Okay, let me write it here itself. So this will become ln E minus IR divided by, okay, so put I is equals to 0. If you put I is equals to 0, it will just remain E there. So E is equals to minus R by L into T. Now take e to the power of this whole. So from here I can say my I comes out to be E by R into 1 minus e to the power minus R into T by L. This is how I got the expression of my current. Now this L by R I can write as tau. I am taking this tau as L by R. Keep this in mind. Different color, solid line, green color. Okay, so keep this thing in mind. Now this I can write as I comes out to be my I naught, which is the maximum current, the steady state current, okay, into 1 minus e to the power minus t by tau. Somewhat similar to what we discussed in RC circuits. Not exactly same. There the current was decreasing, here the current is increasing. And my tau becomes this, and I naught is my maximum current at steady state, that is E by R. Okay, so I was saying in RC circuits that if something is increasing, it will be of type the maximum value into 1 minus e to the power minus t by tau. If something is decreasing, it will be of type maximum value into e to the power minus t by tau. Here current is decreasing or increasing? Increasing. If current is increasing, it will be of type 1 minus type. Okay, therefore 1 minus maximum value into 1 minus e to the power t by tau. Tau time constant changes here because this is LR circuit, so tau is L by R. Keep this in mind. Okay, so keep this formula always in mind that if something is decreasing, it will be e to the power minus t by tau, maximum value into e to the power minus t by tau. If something is let me repeat again, if something is increasing, it will be of type maximum value into 1 minus e to the power minus t by tau. If something is decreasing, it will be of type maximum value into e to the power minus t by tau. It is increasing, therefore 1 minus e to the power thing will be there. So maximum value into 1 minus e to the power minus t by tau, tau becomes my L by R. So if you ask me, draw the curve, how the current is changing here. So I'll draw it. this is my current, this is my time, and this current is increasing from 0, reaching a steady state like this. Okay, this is my I naught. Okay, if you ask how the potential across the inductor is changing, so you can use that L di by dt. I'm not going into that as of now. Okay, now decay of the current. Let us take a condition. Inductor was having some current, okay, and now the switch is closed. Okay, switch is closed. Inductor was having some current initially. Now it is closed with a resistor. So what will happen with time? The heat will be dissipated, energy will be dissipated, the current will keep on decreasing. So if you ask me write the equation, I'll say I is equals to I naught into e to the power minus t by tau. Simple. I'll just write it directly. But if you want me to derive, I can do that. So move in the closed loop, minus IR minus L di by dt, okay, minus IR minus L di by dt is equals to 0. From there I can say IR is my minus L di by dt, okay. So R by L dt is equals to minus di by I, integrating I goes from I naught to I and time goes from 0 to t. This is R by L into t, and this comes out to be minus ln I by I naught, and from here I can say my I comes out to be I naught into e to the power minus t by tau. I wrote L by R as my tau. Okay, so in exam you don't do derivation. Exam just you have to use the formulas. Therefore I was telling you a trick to remember the formulas of RC circuits also and LR circuit also. Same thing. One important thing. Here at steady state, if you talk about at t is equals to infinity, what will be my current? At t is equals to infinity, this term will become I is equals to I naught. Maximum current. What is maximum current? E by R. E by R means like inductor is short circuit. So at t is equals to infinity, inductor behaves like a short circuit. At t is equals to 0, I is 0. It means inductor behaves like a open circuit. Keep this thing in mind. At t is equals to 0, it behaves like a open circuit. And at t is equals to infinity, it behaves like a short circuit. So I'm not writing the same statement again, just I wrote SC, short circuit. This is open circuit. Keep this thing in mind. So what happens? Inductor cannot afford sudden change of the current. Sudden change of the current cannot happen through the inductor. So you are switching the circuit on, immediately the current cannot flow. Sudden change it will not allow. Okay. So current will be 0. Slowly it will increase. Steady state, no resistance, because it is at steady state. Now it's a long time. So at long time it will behave like a short circuit, as if there is no inductor. Okay, now coming to the question. 3 identical resistors with resistance 12 ohm and 2 identical inductors with self-inductance 5 millihenry are connected to ideal battery with EMF of 12 volt as shown. The current through the battery after long time the switch has been closed. Long time means inductor behave like short circuit, inductor behave like short circuit. Now we are having 3 resistors in parallel, so the effective resistance will become R by 3 of this circuit. So if I say the current of this circuit, it will be V by 3R, V by R by 3. So that is 3V by R. So 3 into V is 12 divided by R. What is R? R is 12. This becomes 3 ampere. 3 ampere. Now you'll ask, sir, it is not depending upon the self-inductance value. Yes, it is not depending upon L. It is not required, not needed. 5 millihenry it is given, some extra data is there. Another question, for the given circuit, the current through the battery of 6 volt just after closing the switch. Now you close the switch just after. Just after means t is equals to 0. T is equals to 0 means inductor will behave like open circuit. So close it. Open it. So open circuit. So you can say no current will be there in this circuit. Only current will be through this circuit. How much current will be in this loop? EMF divided by total resistance, 4 plus 2, 6. This comes out to be 1 ampere. Just after, for the given circuit, the current through the battery. So through the battery, it comes out to be 1 ampere. I hope this is clear to you. Okay. Now another question, a coil of inductance 1 Henry and resistance 100 ohm is connected to a battery of 6 volt. Determine approximately the time elapsed before the current acquires half of its steady state. Okay, half of its steady state. I know I is equals to I naught into 1 minus e to the power minus t by tau, and this is my steady state current is I naught. So this is half of its steady state. Half of this steady state means I naught by 2. If you put this as I naught by 2, from this you will get e to the power minus t by tau as 1 by 2. Okay, so it will become e to the power t by tau is 2. So t comes out to be tau into ln2. What is tau? Tau is L by R. Okay, tau is L by R 1 by 100. Okay, 1 by 100 is my tau. So t comes out to be tau, that is L by R 1 by 100 into ln2. ln2 is nearly it is mentioned 0.693. So 0.693. So if I write this approximately, this comes out to be 7 milliseconds. So this I got as 7 milliseconds. Now next, the energy stored in the magnetic field associated with the coil at instant 15 millisecond after the current is switched on. So I will find what is the current after 15 millisecond, and using that current I will write the energy, that is half Li square. Is that clear? Okay. So how to find the current? Time is 15 millisecond. Put the values. Okay, put the values there. So first of all, I am finding, where should I write? Here, I is equals to I naught. What is I naught? 6 divided by R. I'm using this formula, okay, into 1 minus e to the power minus t. T is 15 millisecond and tau is 1 by 100. 1 by 100. So minus t, t is 15 millisecond by tau, and tau is 1 by 100. So into 100, like this. So this will become 15 by 10, which is 3 by 2, and e to the power minus 3 by 2 is given as 0.25. So this whole is getting 0.25. This is 0.25, so this 1 minus 0.25 will become 0.75, which is my 3 by 4. 0.75 is 3 by 4. So I will become 6 by 100 into 3 by 4. And you can say this as 9 by 200. I got my current. Now finding the energy, half Li square U is equals to half into L. What is L? What is L? L is 1 Henry, half L into I square. I is 9 by 200 square. So 9 by 2 is 4.5 square. 1 by 100 square, 10 to the power minus 4. the options are in millijoules. So this will become 1 by 20 into 10 to the power minus 3. So 4.5 square divided by 20 is nearly equal to 1. So it is nearly 1 millijoules. So I can say C is the correct option. This was a bit lengthy question. So if such questions is there in the mains, so better to skip that as of now and then attempt that at the end, because here some calculations are there which may take some time, some more calculations. Specifically the questions having more calculations I don't like actually. The questions which require concepts and other things, they are good. Like calculations questions I avoid generally, avoid in the exam. So if exam is there, so if I see like these 4 or 5 questions are there, okay, which require too much calculations, so I'll leave them. I'll come to those at the end, because if calculations are there, it is very easy to commit some silly mistake. Okay, if logic is there, concept is there, you can very quickly write the equations, derive the final formula of something. That is very easy to do. Okay, the time taken for the magnetic energy to reach 25% of its maximum value when a solenoid of resistance R and inductance L is connected in battery. Magnetic energy is reaching 25%. What is magnetic energy? Half Li square. It means current is reaching 50%. Current is 1 by 2, magnetic energy will be 1 by 4. Okay, so the current will be reaching 50% of the maximum, means 0 to I naught by 2. Current is going like this. Okay, so the current is going from 0 to I naught by 2. How much time it takes? Tau ln2 we just did. So time it takes is tau ln2. What is tau? L by R ln2. We just did this, isn't it? Therefore I am just directly writing it. A option. Just straightforward. Okay, LC oscillations. Now this is one of the interesting part of this chapter, and not many questions in mains they are asked from LC oscillations. Okay, so it's but the interesting part why I'm saying is you can relate this with a spring block system oscillating. You can relate it with that, and you can see, you know, like we are relating an electric circuit to a mechanical circuit basically. Okay, so one energy will say kinetic energy, another energy potential energy, how kinetic and potential energy are oscillating there. Okay, so let us take, we are having a capacitor initially charged with charge Q naught, and now I am closing the switch at t is equals to 0 like this. Cut, I closed it at t is equals to 0. At some instant, let us take here charge as Q plus minus, some current is moving in the loop I. So when I'll move, okay, anyways I have drawn the other diagram also. So I closed it. Now the circuit is like this. At some instant the charge is Q, some current is going like this. Okay, now if I move in this loop, start from a drop is there, minus Q by C. Sorry, a gain is there. I am going from negative to positive plate. A gain is there. I am moving like this. So plus Q by C. Then in the direction of current moving through inductor, so minus L di by dt, and this is equal to 0. Okay. Now, how to relate current and charge? You will say Q is equal, we know that I is equal to dq by dt. But here one thing is there. This current is coming due to decrease of this charge on the capacitor. This Q is not the charge flowing through a cross section. Okay, this is the charge on the capacitor. The capacitor charge is decreasing, due to which the current is coming. So I is equals to minus dq by dt here. So Q by C minus L d by dt of minus dq by dt. So this will become minus minus plus d square Q by dt square is equals to 0. And I got from here equation d square Q by dt square is equals to minus of Q by LC. You remember some equation like d square x by dt square is equals to some acceleration, d square x by dt square is acceleration, and that acceleration is minus omega square x, where it is, where the acceleration is minus omega square x. You remember something like that? Oscillations. Simple harmonic oscillations. Yeah. So simple harmonic oscillations. So this is of form like this, d square x by dt square. What is that? That is my acceleration. Acceleration is minus omega square x. Where? In simple harmonic motion. And we remember, in simple harmonic motion, my x comes out to be of some format, a sine of omega t plus phi. Some form like this it comes out, isn't it? This is 1 by LC. This is my omega square. So omega is 1 by root LC. If I write current Q as a function of time, it will be some peak charge. What is the peak charge? The charge here, not current, I am writing charge Q. So Q will be the peak charge. What is that? Q naught into some function cos or sine, I don't know. So let us take some sine function, omega t plus phi. But I know that at t is equals to 0, my charge Q is equals to Q naught. Put t is equals to 0. Charge Q is equals to Q naught means phi is equals to pi by 2. So I got phi is equals to pi by 2. So this becomes Q naught cos of omega t. This is my current charge, okay, on the capacitor as a function of time. And if you want the current, differentiate it, use this relation minus of this, okay. So cos differentiation is minus sine. So this will become Q naught omega, okay, sine omega t. This becomes my I. And what is Q naught omega? Q naught omega is my peak charge. Q naught omega is my, sorry, not peak charge, peak current. So this becomes my I is equals to I naught into sine of omega t. Current and charge are oscillating sinusoidally. You see, this is a simple harmonic motion. This is not in that much detail in mains, but I am telling you few of the concepts. Here there is no energy dissipation. One thing, there is no resistor, so no energy dissipation. Energy is oscillating between capacitor and inductor. I can consider the energy stored in inductor as my kinetic energy, energy stored in capacitor as my potential energy. Okay, kinetic energy, why? Because there is current, therefore. So that sometime the current is maximum when charge is 0. When charge is maximum, current is 0. So when my kinetic potential energy is maximum, kinetic is 0. When kinetic is maximum, potential is 0. It's like the spring block system. It is oscillating, a block is oscillating like this. At maximum extension, kinetic is 0, potential is maximum. Maximum compression, kinetic is 0, potential is maximum. At mean position, kinetic is maximum, potential is 0. Energy is oscillating like this, changing. Okay, same thing is happening here. Okay, so here oscillations are happening like that. Okay, total energy is same. So at any instant, if you say the total energy U, if I write, that is my energy stored in the capacitor plus energy stored in the inductor. In capacitor, I can write Q square by 2C. In inductor, I can write half Li square. This total energy is constant. This is constant, not changing. That will not change with time. At t is equals to 0, how much is that? Q naught square by 2C. This energy was 0 because current was not 0. So I know this constant is my Q naught square by 2C. At some instant, current is given, you can find the charge at that instant on the capacitor. Okay, or let us take some current is given, it is asked find the maximum charge on the capacitor. Sorry, at initially let us take the charge is given, the initial charge, and it is asked find the maximum current. One thing is you can use that is Q naught into omega. One thing is that either you can use, or you can write my total energy initially is as my energy stored in the inductor. From there also you can get the maximum charge. Okay, we will have a question on this for you. Yeah, a capacitor of capacitance 100 microfarad is charged to a potential of 12 volt and connected to a 6.4 millihenry inductor to produce oscillations, the maximum current. So one way is I can just say I is equals to Q naught into omega What is Q naught? Q naught is my C into V into omega. Omega is 1 by root LC. Put the values. What is CV? C is 100 microfarad. What is V? 12 divided by root of, what is L? 6.4 millihenry. What is C? 100 microfarad. Okay, can we cancel few of the things here? 10 to the power minus, you can say this 10 to the power 2, so 10 to the power minus 1 will remain there, minus 1 will remain there. 10 to the power 3, if you take this out of the root, it will become 10 to the power minus 3, so this will become minus 3 is there, so minus 3 will remain here, so 10 to the power minus 3. If you cancel this will become 10 to the power minus 1, so minus 1 will become 1 by 10, so this will become 12 divided by 1 by 10 I can take inside, so this will become root of 64, which will become 8, so 12 divided by 8, 4 into 3, 4 into 2, this comes out to be 1.5 ampere. Okay. Another way was, as I was saying, the total initial energy stored in the capacitor becomes my total kinetic energy, means the total energy that is stored in the inductor, then only the current will be maximum, isn't it? Yes. So half CV square is equals to half Li square, got cancelled, and L and my I comes out to be V root of C by L. Same thing, V root of C by L. Anyways, root C I could have cancelled here. So this comes out to be 1.5 ampere. And this is all. So not so many varieties, you can say till now it is asked in mains. The simple things are asked from LC oscillations. So this is all, and we have covered all the varieties that are asked by NTA till now from this particular chapter, considering everything in detail. I hope you are able to understand each and every point. If there is some doubt, some conceptual clarity you need, make sure you comment. And if you have reached till here and solved all the questions with me, make sure you comment completed. Okay, it motivates me and I feel like somebody is taking help from these videos. And also don't forget to join the group that is there. You can say the batch that is there on the PW app. So in the description there is a link, click that link. So from there you'll go to the PW app and join the free batch there. There you will access the DPPs and the class notes. Now here I have mentioned all the things, many of the formulas are there. You may not write these things because you can get the notes with you, so there you can access the notes and the practice sheets. So in practice sheets I have a good set of collections, good set of questions for you to solve